Hello, good morning, everyone. Welcome to the Severo Ochoa Thematic School 2D Materials, Oxide Membranes, Twistronics, and beyond. I hope, yeah, they can hear me. So as you probably know, this is the fourth edition of these thematic schools on frontiers in material science and condensed matter. Almost 2 years ago, there was the first school on angle resolved photoemission spectroscopy. There, the main actors were Professor Kylie Shen and Massimo Talarida. Then there was another school on orbital currents in solids. There was a lot of speakers all over the world from Europe, America, and also from Asia. Then it came the third school on Reichba and Berry physics in quantum confined systems. Here there was the contribution of Dr. Annika Johansson, Professor Andrea Caviglia, and Dr. Mario Cuocco. And here we are today in the kickoff of this fourth school on oxide membranes, twistronics, and beyond, where we are extremely happy to host Professor Harold Hwang, Dr. Leni Bascones, and Professor Nini Pryds. But not only this, yesterday we already had an invited seminar from Professor Jacobo Santamaria as a prelude of this school. And there is more to come in this year, so probably we can give you some news tomorrow, but stay tuned. A few words on ICMAB for those that are not familiar with the institution. We are a research center awarded with the excellent distinction since 2015. We are part of a mother institution, CSIC. ICMAB is around 3 decades old, and we are located at the university campus, the University Autonomous University, close to Barcelona. We are part of the Barcelona Nano Cluster, that there are many institutions on it, for example, the Microelectronics Research Center, also the Catalan Institute of Nanoscience and Nanotechnology, that some of you are from there, and we are also very close by to Alba Synchrotron. Regarding the personnel, we are around 400 people, including senior researchers, large amount of PhD candidates and undergraduate students. Here, there is also the count of a spin-off from this institution. These numbers are from 2023. Regarding the research, we can define 3 transversal skills here at ICMAB, classified as the synthesis and advanced manufacturing. Also, there is expertise on advanced characterization and design, theory, and simulation. So we bring these 4 together to tackle some societal challenges, in particular in energy, electronics, and health. Let's go back to the 2-dimensional school. So we have a program of 2 days. Today, the main topic is on single crystalline membranes, where the lectures are Harold Hwang and Nini Pryds. So the idea is that you can interrupt them during the lecture as long as we can keep some flow, right? And for that, we dedicated some short breaks after the lectures in order that you can also ask some questions, and for people online who can place the comments or concerns in the Q&A area. So also, if there is not enough space here to address the questions, we have a large buffer time here after Nini Pryds' talk that hopefully we can actually take all the questions there. I have to say that there is a coffee break after the 2 lectures of Harold Hwang. The coffee break is here exiting the conference room on the right. Then after the morning session, we will do a group picture here at ICMAB. And then there is a lunch break. The lunch is on your own, but I can give you some cafeterias here close by, like walking distance of 7, 8, or 10 minutes. You can scan this QR code if you want to download this slide in your cell phone. We can place it at the end of the session also today. After the lunch break, we have a poster session here at the same place where we will have the coffee break. So yeah, please join the poster session. Nice place to interact, make some connections, collaborations. And there we can also offer coffee and cookies. The second day, we have pretty much the same pattern. Here, the topic will be interfaces, twistronics, moire, combining theory and fabrication and characterization. We will have the lectures from Leni, Bascones, and again, Nini, Pryds. And as I said, we have the same procedure with some breaks, the coffee break, then the lunch, and then we have the second poster session at the same place. And that would be pretty much all. So we like to recycle badges. So please, when you leave the school, dispose your badge at the box that will be placed at the outside the conference room. Okay. So with this, we can move to the first lecture, and I can pass the mic to the chair, Gabriele De Luca from ICMAB.
Good morning, everyone. I'm Gabriele De Luca. I'm a harmonical researcher working here at ICMAB. It is a great pleasure to be the first chair and introduce Professor Hwang. He's actually now a professor of applied physics and also photon science in Stanford University. But before that, he got bachelor and master in MIT and PhD in Princeton, and then became a member of Bell Laboratories before moving to University of Tokyo as a professor, and then finally reaching his current position. He's a fellow of the American Physical Society and the American Arts of Science, and he also got many prizes, including the MRS Outstanding Young Investigator Award, the IBM Japan Science Prize, the Hwang Prize, the Europhysics Prize, and also the McGrady Prize. I think everyone in the oxide electronics community must have read at least one of his papers, being his LSTO, magnetoresistive manganites, and superconductive nickelates, freestanding membranes. So please, Professor Hwang, you can start your seminar.
Thank you. Thanks for the kind introduction. Yeah, I got lost.
No, it works like the pointer has like 2 seconds delay. So
okay. Thank you. A little bit sleepy this morning, I guess. Well, it's a great pleasure to be here. It's my first time at this wonderful Center for Materials Research. I've been to Barcelona as a tourist a number of times. So I'd like to kick off this discussion with some general introduction to the topics of this conference. So maybe, we were trying to do this on and off for many years, actually starting from when I was at University of Tokyo. And of course, you can understand many basic motivations for this. I think we've all, and maybe some of you, are doing research in a number of these different materials families. In the past 15 years, there's been 20 years, lots of opportunity and excitement in naturally kind of exfoliated systems, graphene and so on. Of course, there has been for decades very interesting and steady progress in compound semiconductor heterostructures. I just pick this example for topological states in 2D. And many of us are interested in, maybe I represent this in terms of perovskite oxide heterostructures. And of course, increasingly, at least what I'm felt for the last 20 years, is many of our aspirations in these different materials projections are kind of merging or intertwining together. And so when I was a child, I used to play, I like to build things, and I played with these different toys. Well, surely this is European, so you know this. I don't know if this is more American, but I think the reason I show you this somewhat simple-minded picture is we've all probably felt some of the analogous opportunities and frustrations in the materials that we study. For certain things that we're doing, some are better than others, but there are often cases where you really wish you could mix and interchange and interface these different systems. And so certainly we have this motivation, can we cross-fertilize the techniques that have been developed for different subclasses of materials of interest? And of course, equally, can we integrate them, both for research purposes, but also in terms of developing new device opportunities? And so this kicked us off on this journey that I'll tell you a little bit about in trying to develop mechanisms to both synthesize and study freestanding heterostructures. Okay, so we're going to have a marathon together, I guess. So by way of an outline, I hope this is the pace of the discussion. I'll give kind of a specific or an introduction and background leading to a specific approach for synthesizing these sorts of membranes. I'd like to discuss a little bit about early observations we found in terms of the crystallinity and the 2D limit, and start a discussion and motivate the broad pursuit of strain and strain gradients. So approximately, maybe this will be our break. And I'll go on then to pursue these topics, namely different approaches to use kind of coplanar strain, as well as some discussion of bending and breaking membranes. And I believe there's going to be some overlap of topic with the next speaker. And so I'll just focus on primarily the elastic response that we've been studying. And as was introduced, please feel free to ask questions as we go along. Okay, so despite some effort, it's very hard to feel confident you know the full history of these sorts of things. But let me tell you, this notion of making freestanding crystalline material systems is not at all new. The earliest examples that I'm aware of came shortly after in the 1950s. People found that FCC metals, their atomic positions line up well with sodium chloride. And soon after that, in this very interesting first paper, you can see from the title, Mechanical Properties of Single Crystal Gold Films. And so what they did is they grew a thin film on top of a sodium chloride substrate, and they could directly, squirt water in it and etch a hole on the back side and start to play with the mechanical response of this thin membrane foil. And as you'll see, we'll be very much thinking in an analogy to this, but there are a number of other examples. And just to pick one representative one, there's been quite a bit of work in, say, compound semiconductor heterostructures, for example, where the selective etch has been well developed between different semiconductor components or alloy layers. So these are just some pictures from a review article. The work started quite a bit before that, but you can see also in this field the ability to make and manipulate crystalline, in this case, semiconductor devices. Of course, one of the motivations, not the only one for these sorts of studies, is to make sort of hybrid devices. So integrating, for example, things that you can do best with a fairly precise 3-5 heterostructure in, for example, a flexible holder or membrane or device structure. So how about for oxides, for the kind of systems that we're thinking about? As far as I am aware, if I zoom in on Prof's guides, perhaps the first example is this work from ICMM. There was no pretty picture in this article, so let me just give you the title slide. But what they did was, many of you who study strontium ruthenate know how robust it is, right? And so in this first work, what they studied was a mechanism to completely dissolve the entire substrate, right? So you grow this on a thick typical substrate, dissolve the entire thing away. And as you can see, they're thinking about, say, shifts in the magnetic TC in the system as a measure of the strain effect before and after release. More recently, a group at Argonne National Labs has used these sorts of approaches, and you can see already some rather beautiful structures. This is, again, using this kind of an approach, a large membrane of strontium ruthenate, and this particular motivation was as a bottom electrode, say, for ferroelectric type devices. Another fairly interesting and well-developed set of notions is coming from starting perhaps this paper. A group in Italy that's been thinking for quite some time of making something like MEMS-like devices with oxides. And so in this case, again, using a selective etch between manganites and strontium titanate in this case. I think here this is, yeah, anyway, you can see this undercut etch and thinking about how you can start to make mechanical systems in this way. And subsequently, also very interesting work coming out of the Berkeley lab along these lines. So I should say this is far from a complete list, right? There are people trying to do different things. For example, smart cut ion implantation approaches, other forms that maybe you've seen some papers if you're in this field of on mica, right? So mica naturally exfoliates and trying to use this as a backdrop. But just to give you a sense that even within this restricted discussion, this has a long history dating back some 20 plus years. Now, one of the challenges for us is that compared to, say, for example, semiconductor systems where there's such a large and precise development of mechanisms and ways to selectively etch layers, right? You have this entire semiconductor industry built upon this. You know, in oxides, this is a much less well-developed set of recipes, if you will, right? And so here they're looking at fairly aggressive etch contrasts. And this kind of motivated us to ask whether there was a much more generalizable approach to making freestanding films. And so, of course, this isn't, you know, it's hard to say anything is universal, but a path that we took and I think has been now widely adopted by the field. So the story is actually kind of a funny one. So, you know, if you look at cement, you know, building concrete, it turns out, and I did not know this, my students pointed it out to me, there's a few percent component which is known as this tricalcium aluminate. And it has this terribly large unit cell. I'll tell you a little bit more about this in the next slide. But if you go back, I think, to the 1950s, where this structure was first refined, I think it was labeled in some cases a pseudo-perovskite, as I'll show you. And one of the ways you can already see this is that if I take a slice of this, a quarter of this unit cell in one direction, you can immediately see something interesting. If I put this with respect to 4 unit cell by 4 unit cell building block of strontium titanate in the 100 direction, you can see there's a fairly good correspondence, and there's something better than a 1% lattice mismatch between the two. So somehow this structure is almost like an ordered array of both cation and oxygen displacements or vacancies in this lattice. The way we came about this was, just as an aside, as nicely mentioned in the introduction, we for many years have been looking at this lanthanum aluminate strontium titanate interface. And we wanted, for various reasons, to be able to use a perovskite building block for some of these kind of different polarity interfaces. And we tried to make or metastably make a few unit cells, 1 unit cell of a perovskite equivalent of this. So it turns out that in this target, of course, you can't make bulk stable strontium aluminum O3. That makes no charge sense. This guy, or the strontium version of the structure, was one of our components. And again, I didn't know this, but the person who really led my first student, actually, when I got to Stanford, these initial developments, actually went back and understood some of the opportunities. So to tell you a little bit about more about this calcium-3 aluminum-206, again, it looks fairly complicated, but what's very interesting is that if you look at the subunits of the structure, you have 6-member aluminum oxide rings, right? So if any of you have ever processed or played with devices using alumina, you know, it's a very good dielectric, but it's terrible to process, right? It's very hard to do anything with. So you may be surprised, how can you do some very simple soluble buffer layers using this system? But this is the key point. The aluminum oxide network does not kind of extend in 3 dimensions, but it has this ring such that you can solvate both of these species. Now, what happens in cement, you know, if you go to the hardware store, you buy this powder and pour water in, this particular component makes a hydrogarnet. So water goes in and kind of binds and swells all the other ingredients in your cement. But what's interesting is if you go from calcium to strontium, and even more to barium, you get something of, you know, 20-fold already increase in the solubility of water. And it turns out barium version of this is extremely soluble, even going beyond that. Okay. So these were the starting ingredients. And in terms of thin film growth, this very kind of complicated looking system grows rather straightforwardly and nicely. So first thing I can say is that even at the very earliest stages, you could see kind of unit cell by unit cell growth. This is looking at surface electron diffraction to monitor that deposition process. I should say that these are not unit cells, actually. It's these quarter unit cell charge neutral units that are being deposited here. And so this is a very early example of just saying we masked off an interface or covered up one layer. This is, say, 100 or 200 nanometers of this strontium version of this material. And just dip it in water for a second and blow it off, and you can see it's completely gone. And these components are very nice because then it gives you a surface that is very residue-free, as far as we can see. So maybe not universal, but quite nice in the sense that this gives you an epitaxial layer that grows well on many of our perovskite building blocks, and it can be fully dissolved in room temperature water. So D is the guy that really had these very creative ideas and developed them. And so simply speaking, the system is like this. We happen to be using pulse laser deposition in our nice dry chamber. This is yet basically another layer to grow in some heterostructure. And the point is, starting from a substrate, if we grow this soluble buffer layer and then subsequently grow a film or heterostructure, we can then dissolve this layer off and transfer it onto whatever other substrate you'd like. And so we and other groups have developed various recipes for this kind of stamping, if you will, with various polymers and so forth. We borrowed a lot from the advances made in 2D systems like graphene. But you can see even from the early days, it's a little bit rough, right? These are literally just cut pieces of substrate, but you can see membranes that are already exceeding a kind of millimeter lateral scale. The second point that we and others are starting to utilize is that the advantage of this is you're growing generally on substrates with lattice constants and environments that are really optimized for the materials you want to study. And so this was what D shows here is the growth of strontium titanate, lanthanum manganite superlattices that have been lifted off and transferred. Okay. So that has kind of gone off in many, many directions around the world. And our group isn't very big, actually, but a postdoc at the time, Hwang made this very attractive kind of graphical representation of several of the different directions we'd been going on in our lab. And so this has now proliferated to many more systems, but just representatively, you can do things like magnets, dielectrics and ferroelectrics, doped semiconductors, and superconductors. And maybe at the very end, I'll come back to this point, but of course, many of you know that things like the cuprates are very sensitive to moisture and so forth. And so indeed, we're making heterostructures to protect, an embedded cuprate membrane. And as we grow these different kinds of systems with different constraints and lattice constants, let me just summarize a lot of work and say that we've been using these different versions, calcium, strontium, and barium, to tune solubility and the lattice constants. And to kind of give you a very simple visual graphic of the types of things that we're finding, this was actually just a blow up from that earlier cross-sectional image I showed you 2 slides ago. So this is the manganite titanate superlattice. What I want to draw your attention to is this buffer layer. You see these dark circles here, right? So these are actually dislocation cores. And so maybe, or at least my naive understanding, is that this system is a kind of lower density, right? There's these vacancies than the perovskite nearby. And so energetically, it's often preferable for dislocations to go in this system. And so just phenomenologically, we find that within kind of a % lattice mismatch, things go very nicely. We can release large area membranes. But if you go beyond that, I think many of you have experienced, if you're playing with these things, lots of fracture and cracks, right? To small pieces. And so this is kind of motivating our use of this kind of tuning of the lattice constant of the soluble buffer layer to accommodate that. Okay, so this field is going in many, many different directions, and this is a very small sampling of some of the early results that have been observed. First, as I had mentioned, we're using pulse laser deposition, but this kind of approach and the opportunity to make freestanding membranes is fairly agnostic to growth technique. So here's an early demonstration using molecular beam epitaxy, and as far as I understand, sputtering is also working. Exciting early work from TU Delft at the time, I think, using these suspended membranes as nanomechanical resonators, right? And so a lot of these ideas are building over the last, or had the previous efforts in graphene and subsequently layered chalcogenides, where you have lots of opportunities to mechanically probe and excite these systems. As you'll see, a lot of what I will show you is fairly kind of on the fundamental side. But one of the big opportunities that many people are embracing is the fact that you grow this and can integrate this physically with other systems provides many interesting opportunities for devices and heterogeneous integration. So one, of course, canonical example would be using high-quality ferroelectric devices, say for a memory purpose, that you can grow on this optimal substrate, but then transfer onto whatever you like in silicon or so forth. And these were 2 early demonstrations of this. Maybe 2 other examples that I'll give you here is just to say that there are even different new ways or developed ways to grow this. I think Jacobo described this yesterday a bit, but this notion of remote epitaxy, this discussion of trying to transmit an ionic template across, say, a bilayer graphene interface has been applied to oxides as well. And really, a lot of the themes that we're going to talk about is this incredible mechanical flexibility. And here's an early example of studies, say, in electron microscopy environments, where you take the ability to bend these and stretch them aggressively, and discussing, for example, the elasticity and the domain response of barium titanate in this case. Okay, so with this kind of somewhat brief and broad introduction, let me give you a few focused areas of discussion. And maybe the first question that Sung-Se, the postdoc that worked on this at the time, asked was a very interesting, actually turns out, story, which is how thin can you make these membranes, right? Certainly we have all witnessed and seen the amazing ability and the utility in making 2D systems that are exfoliatable. And so the question is, if I give you a three-dimensional perovskite, what can you do with this? So let me just show you first a few pictures and tell you a story along these lines. So this was an 8-unit cell strontium titanate thick layer. We released as a membrane in the ways that I'd mentioned to you. And we put it on a TEM grid, right? And this is a very simple way to do plan view TEM, right? Almost no sample prep. We can just look right through. And we weren't using a very fancy microscope at the time, but in any case, you could see basically a lattice, right? And the summary statement would be that if we have 8-unit cells, or actually specifically 5-unit cells or larger, this system looks essentially single crystalline over very large areas, the field of view. What was very surprising to us was that if you go just a little bit thinner than that, there was a dramatic change in that image. And so this is just going from 5 to 4-unit cells of strontium titanate. You can see already a very dramatic change where you can see patches of crystalline domains, lots of strange things in between. And going from 4 to 3-unit cells, you can see this, the length scale for crystalline coherence is just rapidly collapsing down. What was most surprising to us was that all of these layers were single crystalline before we released the structure. So we're growing at, fairly high temperature, but somehow by dissolving this interface layer, by releasing this membrane, something dramatic happened. And to give you one way to just kind of sense or prove that this thing was actually crystalline in the initial state, these are, again, surface electron diffraction, read diffraction images of the crystalline buffer layer growing 1-unit cell of strontium titanate, 2 and 3, 4, and through the series, right? And so you can see this very nice kind of coherent diffraction, and yet somehow by dissolving this layer out, we had this abrupt transition in the apparent crystallinity. So what Sung-Se figured out actually dates back or relates to, we think, a very old story. And so this had an interesting history in terms of a very simple-minded question. We'll cast it in our language here. Can 2-dimensional crystals exist? Right? And so back in the early days, under simple assumptions, the conclusion was that you can't have long-range order or crystalline order in 1 or 2 dimensions. And this developed and was codified in the so-called Merman-Wagner theorem, right? Which states that in systems in 2 dimensions or less, you can't break any continuous symmetry at finite temperature. And subsequent to that, there was this interesting development of notions of the BKT transition. And the idea was that actually, if you have a 2-dimensional system, a lot of these early works were in spin models, say for an XY magnet, you can have actually pseudocrystalline order stabilized by topological defects, right? So, vortex and anti-vortex pair. I just show you here. If I map that to our question, whether you can have a 2-dimensional crystal, the equivalent topological defects you might think about are these sorts of crystalline defects, right? And so this has a very beautiful and rich history in physics, and it actually goes on today in searching for systems that exhibit and one can study the 2D melting transition. Very wide range of systems of investigation. So how does this possibly map onto our story? Right? Yeah, there was a funny thing I wanted to tell you about this, right? So if you were a good student and you read your textbooks, then you would say, there's no such thing as a 2D material. And I was on an airplane, this was quite a while ago. And I don't know if you know this, I don't know how to describe the equivalent in Europe, but this is kind of a general magazine. It's not a science magazine, a little bit long articles and so forth. And I found this very long article on graphene, right? So I was flipping through this article, and I think this is a quote from the article. And so the famous guy, Novoselov, right, basically said, we're having referee complaints, right? So if you recall, their first demonstration of graphene was published in Science. And I found reading this that actually they had apparently submitted to Nature, but because of Mervin-Wagner theorem, they said this is impossible, right? So for the young people in the audience, just because you're rejected doesn't mean you'll win the Nobel Prize, but you may not be wrong, right? So I just thought this was kind of funny. In any case, so why or how could you map some of these ideas here to the system of this freestanding membrane? So this is a cartoon image from Sungsei on how you might think about this kind of a transition. So formally, a long-range order exists in the T=0 limit, but at finite temperatures, this system is stabilized by bound pairs of, say, vortex, anti-vortex defect pairs. So as you go up in temperatures, the number of these things grow in some parallel form. And the so-called BKT's transition is kind of when these things unbind and exponentially proliferate. Okay. And so as I'll explain again, coming back to this in a moment, if we look at the crystalline coherence length of these sorts of membranes, you can see what your eyes told you, that the coherence length was very long for greater than 5 unit cells of thickness. And then it kind of exponentially collapses as we go down this road. And what's interesting is you can map this feature right onto these sorts of ideas. But if I extract a temperature scale, a BKT kind of scale out of this problem, you get something like 1.5 to electron volts, right? So why would there be this enormous kind of energy scale in a problem when you simply put this in room temperature water, right? It seems so gentle. Our conclusion was actually the kind of fluctuation energies or the effective temperature of the system is really not coming from the actual temperature of the system, but by solvation, right? So it sounds gentle, but when you think about it, when you dissolve, like you dissolve your salt crystal or something like this, you're really breaking an ionic bond. This is the scale of that bond. So our idea was that as gentle as this may seem, by dissolving this layer out, perhaps what we're doing is taking a kind of a trajectory related to the so-called BKT transition. Okay, so the real transition is a discussion in terms of raising temperature and crossing over, right, these kind of proliferation of topological defects. But imagine what's happening is as a function of thickness, we're really coming across this at a high energy scale. So what would be the kind of ingredients? Maybe this view graph is a little bit too busy, but the topological defects there are going to involve some sort of dislocation energy, right? And so in the thin regime, I can say that that energy scale is going as the Young's modulus times the thickness, right? So as the thing gets skinnier and skinnier, then the cost of this defect is going down, 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 okay? So that can kind of represent this line here. Okay. So what we think has been going on is that we're crossing over, as we dissolve this layer out, we're crossing kind of this abstract phase boundary and catching the collapse of this kind of quasi-crystalline order scale. Okay. And it's natural that this would map to the thickness, as I said, because this is going to now go into that energy cost of this defect. So if you go back to this data, at least, we have a funny issue is this is kind of, discretized in the number of layers that we're making. but certainly in terms of scale, this looks very much like what you would expect for such a costless, styleless phase transition. Okay. So Sung is now at UC Davis. I found this fascinating, and at least at my cartoon level, I could try to understand, how can I live in a world or understand a world where we had this fairly dramatic change in crystallinity, whereas graphene, is a thing, right? It's in this, this is a very simplistic model, by the way, so don't take it too seriously. But if you say then the thing to think about is that perpendicular bond that you're trying to release, you can kind of map out a phase boundary in terms of whether or not I have an asymmetry or equivalence in the bonding strength in plane versus the out of plane. So at the cartoon level for our perovskite, this ratio is unity, right? It's a three-dimensional system. This bond energy is the same as that bond energy, if you will. And so we have this fairly dramatic transition. In the level of graphene, where this is of order greater than a factor of 100, right? So a very weak bond between the layers, but strong covalent bonding in the plane. Again, formally, the physics that we discuss, if we map this problem, then the length scale for crystalline coherence between such defects becomes very macroscopically large and largely irrelevant for the scale of experiments you and I would do. So the organizers specifically had mentioned or suggested this topic, and I'm very glad to, in the sense that we don't know what this is good for, but it seems very interesting to me, right? So we have a system where we can control this kind of crystallinity and orientations, at least at a statistical level. And I've always wondered if things may be a little bit further away from us in electrochemistry or catalysis, these sorts of applications of membranes, this might be a very interesting tool. Okay. I guess I didn't quite realize how this was going to go, so maybe I'll define the boundary later on, but let's see how it goes. Okay. So I told you a little bit about the way you can make this and gave you a little bit of an extended discussion about a specific approach, but let me tell you a little bit maybe before our break, then motivations for thinking about strain. So already in our field, in our community, strain has been an enormously impactful research tool. These are just a few of the examples, but for example, in single crystal, say quantum materials, this is this famous strontium-ruthenate superconductor. By applying uniaxial strain, people found that the superconducting transition temperature can be shifted very quite widely, right? And what was interesting and motivating them was thinking about a different way to probe, for example, the order parameter symmetry in the system. If I remember correctly, Jacobo might have even shown the exact same picture, but many of us in this room that are utilizing epitaxial strain in thin films and so forth confront and use this all the time. That is to say, by providing an epitaxial template, you can stretch and strain a material in a thin regime where it's complying to the substrate. So these are rough numbers, but I would say that certainly on the room temperature scale, this is far less than 1%, so the fracture strain that people encounter. On the case of epitaxial films, of course, the details of the system and the growth matter, but on the scale of 1 to 2, but certainly by 2% for kind of reasonable thickness films, you start to see, say, dislocations, defects, and so forth, right? So there are some bounds to this. And in terms of the membranes, I guess the question is to what degree can we use this very interesting materials geometry to make measurements and new directions in this regard. So I'm showing you here, if I remember correctly, something like 4 or 5 nanometer thick strontium titanate membrane. This is a silicon nitride grid. These are 2-micron holes. And what's very interesting is that, this is a system that is a very brittle ceramic, right? So, if you ever played with a substrate, it's brittle. If you're a theorist, let me say, it has the macroscopic mechanical response of your ceramic coffee cup. Right? You can't really stretch it. So it's characterized by brittle fracture. But look at this. I mean, this thing doesn't look like a brittle ceramic. This was an accident, actually, but you can see that this went down with a wrinkle. So it looks like a piece of cloth, right? And so maybe, I love this picture, actually, but this is kind of captures so many of the opportunities that you have this remarkable mechanical flexibility arising from this geometry. And we and others are trying to take advantage of this, and I'll show you a little bit of the steps that we're making. Now, of course, this is already an issue that's relevant for all of this, but let me make a comment or two in broad strokes first about why this might be interesting. So I saw this slide and asked to borrow it from Puyu and Ramesh. There's all sorts of information and scales here. But basically, I think these guys were trying to nicely summarize some of the energy scales and interactions relevant for complex oxide systems. So there are many details here. But certainly, and I'll give you examples of this, we've been interested in playing with, for example, the scale of crystal field splitting or correlation effects or Hund's interactions. This is kind of in this, let's call it an electron volt scale. And what I liked about this slide is that it nicely shows you, again, in broad strokes, the scale of the problem. If I think about a pentaxial strain, for example, 1%, depending on, who you are, you may say this is not a big deal. Hey, what happened? Maybe it's the break. I don't know. Thank you. Sorry about that. Anyway, yeah, so the point was that a 1% strain is kind of doing on the scale of an electron volt. So if you think about the electronic structure or the systems that you are particularly studying, that's a significant scale. And as I'll show you, and not in all cases, but in some cases, we can really traverse and exceed even kind of this 10% scale. So this is a massive energy scale to manipulate your system. And we're particularly interested in using that to tune or induce new phases, as I'll show you. So that's certainly one broad kind of background statement. The second one, I hope this doesn't sound too philosophical, but sometimes I have 2D materials envy, right? My friends are working rapidly in this field, and at least if I can kind of schematically show my understanding of some of the reason for this rapid progress, is that if you think about starting from, let's say, twisted bilayer graphene as example and related devices, they have so many experimentally tunable parameters, right? There's just a small list, but of course, you can electrostatically gate the system. They're generally low electron density systems, gate tunable, often using boron nitride, so very clean gates. You can also tune the displacement field. So if I have a top and bottom gate, right, I can put a displacement field on and off of this. And so the point is that if I give you these 2 degrees of freedom, and my friend that's a theorist says, oh, somewhere around here, you might find a very interesting phase. I have a wide experimental access to that, right? I can tune these things. And, if you see these, I always get confused, but you see these plots now, these color plots, right? And say some displacement field or doping axis, and they say, oh, this is, a Chern insulator or what. But joking aside, this is an enormously powerful knob, because if we try to do the equivalent thing, let's say in bulk materials first, a bulk oxide, this is a very kind of labor-intensive process, right? And we don't have as much the equivalence of saying, I want to change the, T over U ratio or something like that, right? So we have, I think, a little bit struggled with, how we can contribute or develop tools to go after this problem. And finally, I should mention that what's also interesting is that, of course, a very powerful development, and you're going to hear about these things, I think, later today and tomorrow, is things like twist angle, right? And so this is, of course, in general, a sample by sample discrete thing. It has its own issues of disorder. But, in some sense, this is probably, if I talk to my friends, one of the bugaboos for that problem. That, if I want a very twist angle, I need to make a different sample. It's, so painful. And then, I think, okay, that's not a big deal. And so what would be equivalent? So motivating some of these ideas would be, if I take, Puyu and Ramesh's view graph, I certainly have the opportunity to use strain as something like a continuous tuning variable. So this is kind of a cartoon illustration of the notion, if you've ever taught or took a, developing, band structure, right? From isolated atomic orbitals, you bring systems closer together, they hybridize and broaden out in bands, and so forth in a solid. So what happens if you can literally stretch the spacing of the atoms apart, right? And so in some classroom context, you've probably seen or thought about these sorts of variations as a Gedanken experiment, but perhaps we can do this. And if we have time at the very end of, I guess, the second lecture, we're starting to think about also the symmetry of the strain field, that could be also a very useful tuning parameter as well. And so this was the idea, at least one of the ideas that we've been chasing. And so I'll tell you a little bit about it, I guess, after the break. And so if we conclude at least the first part, I tried to introduce broadly three things. One is some of the history and opportunities of making freestanding membranes of all different crystalline systems, and specifically oxides. I went a little bit in depth in early findings that we see a big variation in the crystalline coherence length as we go truly to the 2D limit. And finally, I started the discussion that we will now, after the break, discuss some of the ways in which we can utilize this mechanical flexibility, specifically in the form of strain and strain gradients. So maybe I'm approximately on time, so I'll pause there.
Okay, we thanks Professor Hwang for first part of the seminar. There's a break of 15 minutes now, so we can make questions, but also postpone it to later. It's not mandatory, but if you really have a question that fits with what has been discussed, maybe it's the right moment. Yes, Gustav.
So regarding the crystalline coherence length in the 2D limit, I think I remember correctly, Xiaoxing Pan has done monolayers of bismuth ferrite. So I think it's possible to grow truly to the single films of.
Yeah, I mean, so that's a very good point. I would say two things. Actually, even in that paper, you can see that kind of in the supplement, if I remember correctly, the length scale is certainly larger than what we see, but it is kind of finite, right? It is not on this kind of
it's
scale.
high resolution, yeah.
And so I don't have a good answer for you in the sense that I don't think we, at least speaking for our own group's efforts, we haven't gone into a very material systematic, right, way across all of these things. One of the things, let me expand on this in a little bit one way. So I think Professor Sasaki, I don't know if you follow this field or his work. He's been at NIMS in Japan for many years. He has a very interesting system, or I think preceding a lot of this. So cases where you have, for example, oxides with a sodium layer, right? This kind of natural stacking motif, right? So they're usually dealing with powder, so maybe not large length scale issues, but they're in a case where they can kind of put this in an electrolyte and release these monolayers and disperse it in suspension. Right? Now, so the same questions came up, and so we spent a lot of time thinking and actually talking even at one point I did with him. And so in that case, what they're doing is taking, say, sodium layers, replacing them with larger and larger, say, ions, right? Organics and so forth. So there I could kind of understand there's this kind of gentle expansion, if you will. And in our case, what we were thinking about is then can we cascade down? What is that strength of that interface energy scale? Can we break that down kind of by analogy? So I would speculate that this may not be the exact same numbers for every system, right? You know, it's a lot to do with that interfacial bond. The other thing I should say is I think speed has a lot to do with this. I'm a little bit jet lagged. I forgot to say one thing that was important. You know, whereas this BKT description does seem to match our phenomenology, let me say that in a formal sense, I don't think that this is exactly what we're doing. In the sense that, you know, at least what I understand is that there, somebody was going to show a video that didn't work, but probably there was going to be this slow etch, right? You can kind of see this thing coming in. That is to say, it's not like the whole membrane is at some finite temperature or fluctuation scale, then you quench it. You actually have a diffusion front where this thing is going. So if I had to speculate, and maybe go back to these problems, I think we all now have our recipes, right? We all know, or at least, again, I'll speak for what we think we know. If we have too thick a soluble buffer layer and that's just really fast, it's kind of a mess, right? And so depending on the material stability, the slower you go, the better, right? And so I also have been wondering, but it's a little bit hard to compare apples and oranges to, you know, what they did there, is whether this kind of coherence length scale would be a function of how quickly we dissolve this. You know, how much do I have a surrounding lattice to preserve, you know, as we go through this?
Do they have something to do with how hydrophilic your material is? Could it just be that the water is damaging the STO, whereas for whatever reason, let's say bismuth ferrite is more waterproof?
Yeah, I think that's a very good point, that there is a lot of hydroxide formation and, you know, surface chemistry going on. I should be a little bit careful to say that probably I don't know enough about bismuth ferrite, but if anything, it's not obvious to me that that should be more robust to this kind of chemistries than say strontium titanate. Yeah. Please.
Harold, very nice talk.
Okay.
I have two comments, question
Okay.
about the development. So you started from crystalline, and then you get nanocrystalline, and then mixture of nanocrystalline and amorphous structure. So if you continue to do it, you will end up by amorphous, or what? What is the? I mean, it's not abrupt. It's a continuous way of changing the things. This is one of the questions. The other one is you're growing it on a surface of a crystalline.
Mm-hmm.
So the crystalline substrate must have something to do with the 2D material that you grow on top of it. So it's not 2D like graphene, in my understanding, that you explain.
Yeah. No.
So it is coming from a substrate which you grow, and what is the relation between this? I don't know. I have no idea. I'm just.
Yeah, no. So no, that's a very good point. And so you know, let's say here we have one layer of strontium titanate living on our buffer layer. It's heterogeneous, but this is a 3D system, right? That's is acting as a substrate for this topmost layer. So this thing is crystalline. There's nothing to worry about stability, et cetera, right? And then whatever is happening, right? We haven't seen or done a dynamics experiment, is happening between starting with this crystalline fine structure and examining what happens if we lift this up and simply take this directly onto a TEM grid. In terms of length scale, you know, this is in terms of unit cells, the correlation function, you know, these are the numbers we're getting is kind of on the scale of 5 unit cells, 2 unit cells thickness, right? So again, the previous discussion was also very relevant, you know, is this universal? Are there ways to overcome it? But well, we didn't spend this much energy for other materials beyond the strontium titanate at the time. Yeah. But I don't know, somehow I feel like it's going to be useful for something somewhere. Yes. 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 Yeah. Mhm. So, mhm. Oh, okay. So now I catch your point. Forgive me, I don't remember the exact numbers, but there's a slight lattice mismatch, right? And so, for example, I think it's reasonable to presume, or at least what I would presume, is that as you start to grow whatever on top of this buffer layer, it's going to conformally strain to that strontium 3 aluminum 206. The usual argument is then you go above some kind of critical strain energy and something has to give. I think the point is that as far as we've looked at, probably not systematically enough, we generally find if we have a perovskite substrate, perovskite on top, the dislocation cores are living in this buffer layer. In a simple-minded picture, I think, the density, the atomic density of this buffer layer is a little bit reduced, right? I have some vacancies inside off. So, if I just say, it's almost like the other part that we were discussing. What is the energy cost of that dislocation core, right? It has to do with the Young's modulus and blah, blah, blah. And so presumably that in general, compared to a dense perovskite, will be lower energy. And so what I would say phenomenologically is that if we're kind of plus or minus 1% for a given soluble buffer layer, often things can work out, meaning we can have apparently clean membranes, we don't have macroscopic cracking and limited defects. But if we go above that, many problems occur.
You check whether they appear in the STO when you are working only with an STO layer on top of the sacrificial layer. Depends appearance or not.
That's a good point. No, we didn't check that. Yeah.
Because if they are there, 1, 2, 3 years, itself.
So I think that's a very good point, especially in thinking about the dynamics of the release. But I would say that, if the resulting plan view TEM that I showed you, I think I showed you just down to 2 unit cells. But basically, that picture I showed you wouldn't be able to generate this read pattern, right? And so I agree with you that this might be relevant for the dynamics and, let's say, the damage or fluctuations induced by this. Actually, it's also a good point that presumably as you vary that soluble buffer layer thickness, then the occurrence are not these things. Yeah, so that could be, yeah.
Thank you so much for the talk. Listening to the speaker, speaking that the temperature
No, we didn't. I mean, at least, well, so the simple answer is no, we did not. Room temperature water, period, right? I think it would be interesting. I would probably want to compare the scales that I could access. So, presumably I have 0 to 100 C to play with, in atmosphere. The question is, if the story is correct, what is that plus or minus 100 C on the scale of kind of 1.5 volts, which we're kind of finding. So it's kind of a question of how much we might be able to manipulate that in terms of dynamic range. But of course, this isn't, I am kind of interested, we're not married to this technique. So sometimes we're using this a manganite layer as a sacrifice, it's kind of, I'm not religious about these things. But in many of those cases, they're acids. So it's not clear to me what would be the best system to maximally change the dynamics of how you're doing, when you dissolve this layer and with what solution, for example.
You think that the rate for
again, a very good question. Yeah, well, you were mentioning you had met Varun. So I would say, he in Jochen Mannhardt's group is probably the one working closest to that kind of regime. I guess, okay. So I'm purely speculating here, right? So if I had a membrane and it's, well, let's call it amorphous, this is almost essentially asking, when are you going to start to do things like solid state synthesis, right? When you're basically going to recrystallize that layer based on this template, right? And so if you ask my guess, then I would assume that that's going to be on, kind of calcining a bulk target kind of scale, right? What's interesting is, again, in the case of this work from Stuttgart, where they either explicitly take something that is has incompatible crystallinity with what's underneath, right? Or I could imagine cases where I have a thick enough layer where, let's say, the lattice stability, is the same on either side. So, one of the things I've been interested in a little bit is learning about, or learning from friends about, is, bicrystal interfaces, right? So a lot of classic, ceramicists, right, have been fusing bicrystals and thinking about specific angles. I certainly think that this is kind of an interesting question that's revisited now in membranes or some of the twisted systems that you've been talking about, right? Yeah.
There was a universal question. Yeah, okay, for sake of time, but then can you pass the chat to Janine?
Yes. Oh man, if so we could have had a break if I had stopped talking. For the future speakers, be aware. Okay. So let's keep going, but I'm not sure I'm allowed to say this, but if we collectively decide we need a 5-minute break, I have no problem with that, right? So this could either go 5 more hours or 40 minutes. So either way is fine. I hope you don't mind I said that. Okay, so let me continue our discussion and tell you about things going on in the field and in our group in terms of strain. So I'll focus on earlier work in coplanar strain. And hopefully I'll come back to the end where let me treat this a little bit selfishly like a conference and show you some things that we're working on in the lab. And in between, thinking about both bending and breaking membranes. And so I think Nini's going to show also a little bit about bending. So I'm going to focus my remarks on studies we've been doing on the elastic response. Okay. So let's get going. So yeah, let's say you've worked hard, you've made a freestanding membrane, and you see, yes, it would be great to do studies in terms of utilizing that mechanical flexibility. So many fantastic things are going on. Our lab, a lot of what we're doing is also transport and these sorts of things. So we, have been thinking hard about making large area membranes and uniform strain configuration so we can kind of do transport that we can interpret. So that has been a little bit of our goal. Okay. So again, it's one of these journeys that is, a little bit of a surprise, a little bit in ignorance, but a key statement is that most oxide membranes adhere very well to polyimide substrate. So literally, if you buy a thin Kapton tape, and generally that interface adhesion is good. And so I think that statement captures both the opportunity and the challenges of this. If I say the adhesion is good, and I'm going to show you data where we can stretch a membrane up to, like, say, 10% without slippage, that means there's really chemical bond formation at the vertical direction. The challenge, though, then is, it's a very different world from van der Waals surfaces, right? And so that discussion was a little bit, if you were here yesterday, about, how I can think about these sorts of interfaces. Okay. So nowadays in our group, we're often using a few unit cell template layer of strontium titanate, and then growing whatever else on top. So certainly in that case, this is quite universal, I would say. And there are little tricks that some of our group members have found that for other systems, maybe just a little bit of like a plasma oxidizing that surface makes that adhesion very strong. So the schematic is very simple, but I think it's working pretty well, that we can laminate a membrane onto these sorts of Kapton sheets. We can stretch or apply stress in the far field. And these are finite element simulations trying to do some version of making this homogeneously uniaxial as possible, and this little square is a sample, or biaxial strain, right? So we haven't really explored this degree of freedom, but I think, again, this is an interesting opportunity, right? If you use hydrostatic pressure, well, it's, ideally it's hydrostatic. If you use lattice strain, it follows the symmetry of the lattice. So in principle, if you told me, if you had some theoretical idea, put a strain in this weird random direction, that degree of freedom exists. And we haven't really quite used yet, but I'll show you some stuff at the end. So kind of generation one of these sorts of experiments, at least within our group, was to do the following. We have kind of a little crude assembly. We're stretching these things, looking at it under an optical microscope. And the whole thing is sitting on a hot plate. And so we're using a kind of a low temperature adhesive that kind of solidifies on the scale of 50 degrees C. And so we literally freeze this thing and then go around and do our measurements. So this is an optical image. I think this was a manganite membrane, but in any case, you can see that the scale bar is pretty big. It's a large membrane. And this has been stretched and adhered in the way I just described to you. And again, it's quite a dramatic length scale change in terms of the energies induced. Okay. So, of course, it's one thing to see a macroscopic strain. It's another question to ask what is happening microscopically. And so for that, it's quite convenient to do, obviously, X-ray diffraction, but doing this at grazing incidence so you can kind of maximize the sampling of this very small volume. Okay. So this is an example of this manganite membrane assembled, as I told you, about 50, 80 degrees C. And this is probably one of the early, most dramatic examples that I can show you of having an enormous ability to elastically respond to an applied stress, right? So this is the lattice constants, and these are the visually identified nominal strain versus the stretching of the lattice constant. Okay. Now, if you did this with a single crystal piece, right? When I was a grad student, I would play with single crystals of manganites. So believe me, you can't do this. And even by going kind of on the scale of 30 nanometers or so thick in membrane, those statistics of fracture kind of rapidly approach bulk values. So this thing kind of drops below 1% of order. And so later on in this discussion, I'll tell you a little bit about more about why that is possible and how to think about that. But now, this was kind of the first serious study that Seungsei had done using this system. So I think there's lots of expertise, certainly in this institute, in terms of studying the manganites. So this is a system that has a famous insulator to metal transition, a large magnetic field dependence or magnetoresistance associated with this. And in the paper, you can find biaxial strain. This is, uniaxial strain, but this is for biaxial strain. So first to say that this is also possible, we can stretch in the two directions. This is now a grazing incidence scan in the two directions. So there's a little bit of a jitter here, but this was us trying to go down this diagonal direction. You can see that, going from 0, 1, 2, 3, 4% or 5% strain, you can rapidly suppress the metallic phase all the way to base temperature and undergo a metal insulator transition. So if you know the world of the manganites, this is kind of not surprising that the whole phase diagram, this is a function of doping, for example, from manganese 3 plus to 4 plus. All of these complicated ground states are insulating. Just this pink region is metallic, right? And so you can fall into all sorts of different charge and orbitally ordered phases, right? And naively, we were thinking that there might be some analogy to playing games with the tolerance factor. Again, something well known to many of you in many different perovskite systems, but using the fact that we're often dealing with distorted perovskites, by changing the ionic radius on the A site, you can kind of twist and turn the octahedra and change the electron hopping bandwidth in the system. So in this particular case, what we found was actually a very rich phase diagram. This is all in one membrane. It's a rather tedious thing, I have to warn you. We set the strain stage, do whatever experiments we want to do, go back up to a little bit above 50 degrees C, and then restretch and set everything. And you have to be a gambler because you want to do all of this without breaking your membrane, right? So I will show you after several years, we think we've made some progress on this at the end of the talk. So this system sees a rapid suppression of the ferromagnetic transition. And in fact, we found this kind of new, I don't know how new it is, but I'll show you in a moment what we think is going on, insulating phase. And again, very reminiscent of the competing instabilities in ground states in the manganites. This is actually relatively fragile to melting under magnetic field. So this is, for us, unmeasurably high insulator, but just by putting on a few Tesla magnetic field, you can suppress this insulator, okay? So again, that phenomenology is not dissimilar to what you see in other manganite systems. So we were working with a number of computational theoretical friends on this paper. And the conclusion of the study is as follows. Again, qualitatively, maybe not a shock that this metal insulator transition has very much this flavor of this aspect of the phase diagram that when you have a ferromagnetic metal, you know, this system is kind of trying to maximize bandwidth, minimize things like orbital splittings and so forth. Once you've decided to become an insulator, then, you know, Jahn-Teller effects, orbital ordering, these sorts of things kick in. So the notion is that this is kind of the specific manifestation of these sorts of patterns in terms of the density functional theory that my colleagues had done. But just to describe a little bit without going into the details, this is a difference in energy between the metallic state and the insulating state. And surprisingly, at least within you know, the sampling of this crossover strain is fairly close to what we see experimentally. And so what you see here is the gap for the antiferromagnetic insulator, right? It keeps going up. And the point is we hit a metal insulator transition when this phase becomes more overall energetically favored than this phase, okay? So this is kind of exciting for us that this is an example of using strain to tune, hopefully, some of these competitions on fairly large energy scales. A second example, going back to strontium titanate, is to see what happens when we apply uniaxial, in this case. I'll show you tensile strain for these sorts of membranes at room temperature. So in this work, what I'm showing you here is piezo force microscopy. And this is literally just looking, you know, if you say, I don't see anything here, that's the point. Nothing interesting is happening. At room temperatures, we go from 0 up to over 1% strain. But suddenly we go from 1.25 to 1.5% strain. You see lots of signal and contrast in PFM, right? And so this signals the onset of ferroelectric domains. So I should say that there's been a long history of using strain and pressure and isotope, and et cetera, et cetera. So this was presumably somewhere where we thought, again, we would have this instability nearby. In addition to PFM, actually in collaboration with people at the Molecular Foundry, quite close to us across the bay at our Berkeley lab, there's one also studied as a proxy for the onset of ferroelectricity, the breaking of inversion symmetry by using second harmonic generation, right? And looking at the symmetry of that response. But what was convenient for us is whereas we could only do PFM, at least within our group, at room temperature, this gave us a way to chase the onset of ferroelectric order along this channel. And it's quite dramatic, actually, right? So you can see here, these are the samples or the ranges that we could access with these sorts of experiments. Let me be clear and say this is not theory. These are results of a model extrapolating out. And by something like 2.5% strain, we're inferring TCs of on the scale of 500 Kelvin, right? So again, a pretty exciting opportunity to use strain to access in one sample multiple phases. So I want to now tell you about, in parallel, things that were going on. Again, simply speaking, we were spending so much energy straining things, breaking things, right? Wondering why they break, that we kind of were forced to learn a little bit more about mechanics and how to do nanomechanical testing. And a lot of what we're doing really benefited from the fact that when we started this, the community had just spent, quite a long time taking advantage of graphene and then layered chalcogenides, of both having accessible, very interesting 2D systems and mechanically playing with them. So a lot of what we were doing is very much piggybacking off of that built-up of knowledge. So one of the ways that, say, the graphene folks initially mechanically probed graphene was in drumhead membranes, right? So those holes I showed you, these silicon nitride holes are perfect drumheads, and I'm going to tell you about things where we poke around on these sorts of holes, okay? So kind of to set up a discussion about some of the things we found, let me just remind you, I say remind you, but I had to learn all of this, I have to say, about thinking about simple elasticity and linear response, right? That you apply some load, and then you look how the material responds, and the summary statement would be that if I have some material that's purely linear in a local regime, then all I kind of need to know is the bulk modulus, the Poisson ratio, and I can kind of tell you how some material is going to deform upon some load, right? So even in a bending geometry, you can kind of section this thing up and define that way. So this statement is another way of saying is that the energy density of this system is just going as that strain, right? That local strain that you can calculate. So for quite a long time, actually, maybe initially more as an intellectual exercise, people had speculated about thinking about nonlinear elasticity, right? And so in the context of what I just told you, free energy that goes is like this in strain squared, imagine you just say, okay, I want a Taylor series expand that term, right? And the next thing that you would encounter in that kind of expansion is a strain gradient squared, okay? So lots of prior discussions along these lines. These are, again, this picture that I like very much. These are the drumhead structures that we're looking at. And so we're going to use an AFM in order to do metrology on these sorts of structures, right? Poke around. And specifically, the data I'll show you is thinking about applying a force and measuring the deflection. So if we think about this kind of simple geometry, we have some, finite thickness slab, and I bend this guy because I poked it with an AFM tip. You can imagine that this side is compressed, this side is elongated, so the strain will vary across the thickness of this membrane along this blue line. And of course, this difference in strain divided by that thickness gives me that strain gradient component, okay? And I'm going to skip fancy notation and just remind you, or the strains and the gradients I'm talking about, this is the most significant gradient term in our specific problem. Okay, so a lot of this work was all led by Varun, who's now at Max Planck Stuttgart, as I previously mentioned. So let me first show you a simulation that he had done to explain how we can think about this problem. So imagine you have a drum head with some rigidity and et cetera. And I poke this thing a little bit. Most of that rigidity, this is basically a probe of the bending rigidity, right? So I can color code that term in red here. But now imagine I poke harder and harder on my drum head. At some point, you're stretching, that drum head material. So this is to say that more and more of the energy involved is in stretching this blue stuff as much as it is bending, okay? So this is an imprecise measure, but this is taking as a measure of the relative contributions of bending versus stretching our membrane in terms of this gradient squared versus strain squared. So what is the point of this discussion, or how will it manifest in our experiment? The statement is that if I, again, poke my drum head just a little bit, I will find that the force applied leads to a deflection. And this is kind of a linear response. And the details, this prefactor has various geometric things in it, right? So this is the Young's modulus. This is the pretension. So did you stretch the membrane before you put it on the drum head? Poisson ratio, and geometric factors. Okay? The interesting point of this is that if we go to this stretching versus bending regime, we'll induce kind of a nonlinear response in this force deflection curve. Okay? And again, if I have a simple linear elastic medium, again, similar factors, it'll be the same Young's modulus. Okay. So I'll justify it in 1 or 2 slides later, but let me just relabel things and say that for whatever reason, I'm going to worry about the possibility that the Young's modulus in the linear regime is different from that in the cubic regime. Okay? And again, pretension and bending terms in linear response, and symmetry allowed, the leading order nonlinear response is going cubically in this displacement. Okay, so here are the references. Again, a lot of this built on things that people developed initially in, for example, graphene experiments. Okay. So in fact, if you look at the literature in simple systems, people study and use this, to pull out these things. I forgot to mention that this is for center point loading. So if I have a circular drum head, this is for poking right dead center. There's no simple analytical forms if you go off center. But the point is that if I then do this experiment, I want to, as I've told you, consider the possibility that the Young's modulus measured in cubic response is different from linear response. And I also don't know a priori this pretension. And so the way you can get around this is then to do, in linear response, an extensive mapping of the force deflection curve. That is to say, you go around your drum head and poke in all different places in order to basically collect a 2D map of data from which you can extract and separately deduce the modulus and this pretension term. So having done that, now if we look at poking a membrane, these are different membranes going from 100 nanometers thick to skinnier and skinnier. Of course, when it's thick, it's hard within, the limitations of your experiment or the cantilever forces you can apply. We're just in the linear regime and what we can access. But when we get skinnier and skinnier, you can see this crossover from linear to cubic term. Okay? And so that's the experimental way we can actually try to make the kind of experimental summaries that I'm about to show you. That's how we're going to extract all of these guys. Okay, so what did we find? So we found lots of structure in the way the Young's modulus varies as a function of thickness. So for reasons I don't personally totally understand, many materials have strong deviations from the bulk value on long length scales. Okay, so the fact that this is much softer, if you will, than bulk is maybe not such a shock. What's weird is I've never seen data for a single component system where you have this kind of abrupt non-monotonic behavior. So the point is, in red is the Young's modulus extracted from linear response. Again, this is dominated by bending deformations. And then just when we are thin, we can experimentally access a separate probe of the cubic nonlinearity. And we see a different Young's modulus apparently between the two. Okay? And this is sizable. It's about a factor of 3. And so again, to give you an intuition, if you've ever played with a toy like this, this is a system that's much easier to stretch than bend, right? There's a bending rigidity based on the engineering structure, right? But why should a 3-dimensional cubic perovskite that's just in a little membrane have this asymmetry? There was one key thing I forgot to say back here that I'd like to come back to. This gradient term, this strain gradient term, right, this bending that I told you about, what's important and lovely about these membrane geometries is their contribution to the free energy is scaling as 1 over the thickness squared, right? And so it's kind of consistent with your intuition that it's easy to bend this floppy, thin material around, but this is actually quite relevant for why I think we have many opportunities to go after new things here. Okay, so this has triggered this reminder that we have this gradient term that may be at play. So why do we have a difference between bending versus stretching this material? Well, I should say, formally speaking, experimentally, we can't distinguish between different contributions that would have the same kind of symmetry response. I guess this is a local person, but anyway, there's a nice summary of these sorts of considerations. So lots of things going on. You can have electronic effects, you can have surface piezoelectricity, and in general, if I have a nonlinear elastic response, they will show up as this kind of gradient term. But of course, in our material and in our field, flexoelectricity would be an important candidate. So that is to say, if you're not familiar with this idea, is that if I give you any material, let's say it was centrosymmetric to start with, applying a gradient breaks that symmetry, and then you can induce a polarization, right? So you can induce electrical dipoles, say in a dielectric or an insulator, that is purely coming from this gradient term. So what's interesting is that if I think about this difference of having a cubic Young's modulus versus a linear response measured Young's modulus, if I express that in terms of being purely from some effective flexoelectric coefficient, it will go again as 1 over thickness squared, and it'll have these sorts of terms. So what does this tell us, right? It tells us that Of course, these numbers matter, but if I go from the thick to the thin limit, I can go into a regime where the total kind of elastic energy can be of order 1 contributed by this flexoelectric polarization because we're in this very thin geometry. So more recently, and actually I guess with local help now, I think from Berkeley days, but in any case, if you believe that indeed this should be or could be of dominant flexoelectric origin, how would you go after that? Well, one thing you could do is to go across the paraelectric to ferroelectric transition, right? That's where the dielectric response of the lattice maximizes. And indeed, in this lovely system that we got to play with, this has been compositionally tuned for an ordering temperature a little bit above room temperature. And again, if you take this kind of difference between linear and cubic response, you have a nice peak associated with that ferroelectric transition. So that is to say that this is not the only thing that can be going on, but this clearly indicates that we can generate and design, if you will, the mechanical response of these sorts of systems kind of using these gradient terms. So it's, I think, quite an exciting broad opportunity. So now I'm going too slow. Okay, so I'll speed up a little bit. Let me say the following. So we've been poking and bending our membranes and so forth. And what happens if you poke too hard is obvious. You can fracture your membrane. And so it's a little bit sad, this picture, but I'll show you it's very, very useful. So this is one of these drum heads where we've crashed through with our AFM tip. Okay. As I said, we've been trying to stretch and strain and bend membranes, and to learn a little bit more of their properties is quite useful. And so Varun also took on the study of the statistics and aspects of fracture. So these are very old ideas already, but in case, again, I'll just keep with STO for now. We have one of these membranes. The idea is let's just push, 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 ideally with a simple geometry, like a simple radius of curvature tip. This is his simulation of the strains involved just under the tip. You can see it's very focused there. And let's think about measuring the statistics of fracture. So the nice thing about these hole arrays and membranes is that you have lots of holes, right? So it's not as tragic an experiment as it sounds, but literally go and break, 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 break each one. And so this is, for example, for a 4 nanometer thick membrane. This is a measurement of the probability of fracture versus the force at fracture, right? And different thickness membranes you can pull out. Okay. So how to discuss this? So we don't know microscopically what is the typical kind of defect or flaw that induces a fracture. But even without knowing that, there's been a kind of developed set of ideas that if I have some flawed distribution in my material, it's really the extremal ones that are statistically governing when we fracture, okay? So yeah, let me skip the details and just say that these fitted lines follow this so-called Weibull statistics, right? And there's basically just 2 parameters that are relevant. One is this overall scale parameter, but the so-called M-shape parameter is very interesting because it's essentially the sharpness of this. So if I take this 3 or 4 nanometer thick membrane, what this is saying is that somehow statistically, almost all my membranes break at the same force, right? Whereas as it stretches out, this is saying some of my membranes break early and some break at a much higher force level, right? And so the higher this M value, the higher the predictability of failure. So whatever, underlying statistics and distribution of defects we have, this characterizes their contribution to fracture. What's interesting is, if I plot the results for strontium titanate membranes in the context of things from from MEMS to nanotubes and graphene, it's actually got quite a decent shape parameter in terms of the predictability of failure. So the second set of experiments that he did was to then do the following. He said, let's go sit at 85% of the mean fracture stress, right? And go wiggle it. Just sit there and wiggle it over and over at times, like 1 billion times. And so, okay, so this is not, we're not really a testing lab, but out of many membranes studied, we only see one fracture. You can see we're wiggling, 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 and suddenly it broke, okay? But for all the other ones, what was very interesting is it confirmed kind of what we intuited and what I told you before. That is to say, after this fairly aggressive mechanical testing, and you go back and just ask, how does my membrane look like mechanically? The force deflection curve, it sits back on itself. That is to say, as far as we can see, there's very little evidence for plastic deformation or anything like that. This is a system characterized by brittle fracture. So it elastically responds or it breaks, okay, to summarize simply. And it's interesting. So two things are interesting. So we can map these things out. But why I think this is quite useful and I a little bit wanted to advertise is it's fairly useful to be predictive, not in precise numbers, but approximately. So all of this thinking is built on the assumption that if I give you a material and it's all the same quality, then the statistics of fracture scale is the volume, right? If I have much less material, I'm going to fracture less, right? So I told you before that if we had a thick membrane or a single crystal, the fracture occurs below 1% strain. But we can stretch this thing up to, in that case, 8–9% strain. As far as I understand, to leading order, the issue is simply that our membranes are much thinner, or there's much less net volume, and there's a simple relationship that governs the fracture stress statistically occur in terms of their volume ratio. And again, it involves a sharpness parameter. So it's a little bit useful in the sense that it can give you a fairly easy way to test and figure out basically what is kind of the available range of strains that you might be able to encounter on an experiment. Okay. Hopefully now I wanted to show you some new things. So this is work in progress, a little bit half-baked, but hopefully you might be interested. Okay. So earlier in the talk, I had told you about the strain experiments, right? We had found out that somehow Kapton is a very good adhesion or interface adhesion. We stretch it and do this painful exercise. I can tell you another referee story. Sungsei's paper was well received, and the referee says, oh yeah, could you just do it again for uniaxial? I forgot the details, uniaxial strain. That was like another 18 months of his life because, you know, it's really a tough experiment. You go there, collect data, oh, it broke, start over again, right? You know, so that's kind of a tough way to make a living. And secondly, we got hints that there's some very interesting phase transitions in even zero temperature limiting phase transitions that we want to access. And this is very discretized, right? So basically, Bai and Shin and a couple of my group members, or now former group member, did an amazing job translating this assembly. So as I said, this is kind of this big on top of a desktop to compress it down into various geometries. So we're actually working on a lot of strain stages for different probes. This was the most challenging one. And they basically miniaturized this whole thing. Skipping the details, they have a mechanical axis coming up the top of a probe, right? And so kind of a pulley system, so we're kind of stretching this Kapton. And so, you know, obviously we'd like to get or minimize these sorts of considerations. But as far as we see empirically, this kind of having a soft mechanical strain or stress transfer layer is really useful. Right? Because this is still, you know, a ceramic. And so if we directly glue down the edge of one of these things to something hard, that will fracture in a moment, right? So I think there's something a little bit accidentally we stumbled on in the soft mechanical boundary conditions that we can utilize that's been pretty useful. What that means is that we need very large, relatively large forces and large translations, right? So it's kind of beyond the scale of piezo stacks that are quite popular nowadays. So anyway, so they built this miniaturized assembly. It all sits inside, I think, 21 millimeters or something like this. And also stuck in a camera inside of this. So we could do everything that I showed you before, but we can do this now cold. So you can be at 2 Kelvin, varying field, and so forth. And so the last, let's say, 5 minutes, or maybe slightly less than that, I will take with work that Bai is doing right now that's, I think, exciting in the sense that it gives us the first taste of the opportunities that this affords. So let me briefly introduce, or reintroduce, I think, to many of you, this long-standing issue in cuprates. Namely, if you look at the 214 cuprates, there's a glitch in superconductivity. If you go from strontium to barium, this goes all the way to 0, for example. But you have an anomaly at particularly prominent at 1/8 doping. And it's been understood to come from a competition, if you will, from a competing stripe-like instability, okay? And so this has been something that has been, including using strain, a subject of much discussion and research interest in the past few years. Okay. So Bai, having designed this beautiful strain stage, was using it to study this problem. So he made a 1/8 doped 214 membrane. And this is a typical sample. So in general, we're using inline doubled up or van der Pol geometry. So here's a kind of a van der Pol picture. And what he's doing is basically getting into a regime of basically uniaxial strain, so stretching in this direction. This is a finite element simulation. And this is using our little microscope inside to chase what's happening in the 2 directions. So the point is, if I stretch this guy in one direction, the red curves, indeed, you see this thing stretching, but we have free lateral boundary conditions. So by stretching in one direction, it slightly compresses in the other direction by Poisson ratio, right? And so you can kind of see that here in the blue direction, okay? So cool. Now he stretches this cuprate membrane. And so what you see here is in red here, this is an unstrained state. It has a superconducting transition, as you'd expect. And now we're going to take this red trajectory. That is, we're going to probe the resistivity in the direction along that tensile strain. This is the raw data in the sense that you can see 2 things. TC is being suppressed, but also the normal state resistivity here is going from metallic-like to insulating. And so kind of qualitatively not a surprise. I stretch this thing out. The overall scale of the resistivity is going up, and we also see TCs being suppressed. If we look in the same device, in this case, in a van der Waals case, in the transverse direction, that is, we stretch this direction, but we measure in this direction, we see 2 things. One is the normal state resistivity goes down. Kind of, again, intuition is reasonable that we're bringing all in that direction, the atoms closer together. But also TC is coming down. And so I just show this here normalized. So this is an excursion from 0 to about 2.58% strain. Now, if we, go back to this, clearly one qualitatively different thing is not just that we go from metallic-like to insulating-like in this case. You can see that TC is broadened out. We kind of approach this 2-step transition. And actually, this is totally reversible. We can go back and forth and get back and forth on this. Okay. In the interest of time, I think, at least for our eyeballs, this is quite characteristic of well-developed set of ideas and phenomenology. Maybe I'll show, just talk you through this picture. Mesoscopic or artificial systems where you take a superconducting array of puddles and an underlying metal, in this case gold, and I think this case it was gated graphene. So the idea is in this kind of situation, you often see a two-step transition because first the puddle or the niobium island here goes superconducting, and the second transition is when there's global phase coherence via the proximity effect in the gold film. And so both in artificial systems and in naturally occurring systems, you can see this kind of game in LAOSTO. Again, the onset of first local superconducting puddles and then global phase coherence is kind of the things that we think we're seeing here. Here's what's puzzling or interesting, I think. So all of what I described to you so far was stretching in the 1O direction, okay, along the copper-oxygen-copper direction. Okay. Let's just simply do the same experiment again in the 110 direction along this diagonal. So different, okay? Just to summarize, what we see is an isotropic response. We have a suppression of superconductivity, whether we're in the stretching or compressive direction, and we don't see any of these two-step features. So our working hypothesis right now is that the reason for the response being so different is in terms of the contributions of the strains being generated, and in particular in the context of this charge ordering instability. That is to say, you know, let me just put my own interpretive words, is that if we have a situation where we have a stripe phase and superconductivity and they're doing something like this together, does strain either stabilize or destabilize that stripe instability? So we think this might be what's going on. So, you know, again, a working thought, and, you know, in my neighborhood, lots of interesting people to discuss with, and in the broader context of the cuprates, where there's been for decades this interest in having or thinking about the relevance of these sorts of stripe-like fluctuations, we think what we're seeing very much maps onto this phenomenology, right? So that is to say that if I go in the direction where I have this competition enhanced, that we can traverse a phase diagram where we're stabilizing or increasing the stability of these competing stripe-like phases. And one of the things that's intriguing for us right now is there is this region where we can kind of have a quasi-macroscopically one-dimensional like superconducting instability. And what is the microscopic nature of this system? So as I said, I just wanted to squeeze in something new, something working. Let me close and just say in this second part, try to tell you about our kind of first generation efforts to use strain to induce phase transitions. So this is a figure from the manganites. I told you a little bit about how these kind of nanomechanical probes have really revealed interesting and dominant contributions from strain gradient terms, especially because the scaling with thickness is so favorable. Told you a little bit about the statistics of fracture and the opportunities that we have in these sorts of experiments. And finally, I tried to show you a little bit about work we're doing right now to make that very painful experiment a little bit easier, right? Because, you know, fracture is also, you know, temperature matters. And so even if you look at these single crystal reports from strontium ruthenate or YBCO, they often report, which is natural according to the story, by going down to low temperature apply strain that can enhance that kind of critical strain by factor 5 or 6 or so forth. And so that again should extend the window we have to explore these parameters. So thanks for the marathon. I'll close there.
Okay, perfect. Let's thank the speaker. So yeah, now we will have some time until we have the coffee break, and also to the people online, just write down your questions and I will read them out.
Thank you for the nice talk. I have been following your LCMO work for a long, I think, and I had some question, maybe very silly, but I wanted to ask you. You are regarding this stretching experiment you are doing with LCMO. So when you are stretching, you are doing with a Kapton tape or a polymer with,
Yes.
right? So in this case, when you are stretching, like for example, you put 8 or 10 unit cell of membrane.
Okay.
So do you think when you are stretching, the first layer, which is just top of the polymer, and which is on the top,
Okay.
they are not in the, because you are calculating the strain percentage according to your Kapton 1. So do you think is the really the membrane is facing the same amount of strain, because there could be a strain gradient, and do you think that could play a role?
Yeah, no, that's not a silly question at all. So indeed, conceptually, this is quite possible. It turns out that at least if we take the numbers we deduced from these mechanical measurements, so, let's say 5 nanometers of a manganite sitting on, I don't know, 12 microns of Kapton or something like that, they're kind of mechanically equivalent. And it turns out that this, how should I say, you're kind of envisioning this is a very, very minor feature in this case. But I will give you another example. Sometimes we're thinking a little bit, or I have friends trying to play similar games with moly disulfide or layered systems. In fact, that can be the dominant thing. So you just described doing this, but you can also self-exfoliate. So if I stretch the bottom layer, this thing can just propagate up. So, okay, it's not here. Yeah, on my computer, at least we have a little bit more now experimental probes of kind of that lattice constant variation. So another version of these sorts of things we're utilizing is to do in situ strain under X-ray scattering, like in synchrotron environments. So I can, well, believe me right now, and I can show you later that I think that looks pretty good. But certainly this is a function of the geometry. So it's not generically impossible. What you say absolutely does happen. It just turns out to be a minor contribution for the geometries we're using.
This will not be a big factor if there's two different scenarios. One is you are stretching with the Kapton one, and suppose another one you are just with a suspended membrane or like a drum, and you are doing this. These two scenarios would be like similar and kind of same results, you think?
I'm not sure I catch all the aspects of what you're saying, but like in the manganite case, we don't, because it's a metal, we don't see or think that there'll be these big gradient terms that I told you about in strontium titanate, right? So that is kind of fairly, I think, accurately modelable. I should say, and I kind of pulled it out in the interest of time, there are other ways to do gradient terms. So both we and others have been doing wrinkles and periodic wrinkles and these sorts of things. So if your interest is to generate gradient terms, there are actually many exciting opportunities coming for that, where people can put fairly large strain gradients in a well-controlled fashion. Yeah.
Thank you.
Sure.
In some cases, when you have geometries, as you have shown with in one example with barium titanate, you can have very robust materials against fracture. But maybe we can expect different behavior if we have a planar geometry. At least when we have investigated, we in general, people in literature, films under tensile stress, there is usually formation of cracks when the strain is maybe less than 1%.
Okay.
The thickness is maybe 10, 20 nanometers. But this appears to be different in the case of the membranes that you strain.
Okay.
I don't know if the difference, if the strain is really propagated, if the difference can be because stress is uniaxial, or I miss something.
Okay, just to clarify, the system you describe is also membrane or single crystal?
I would think that we have a heteroepitaxial film, even of material related to those you have shown, Pryds or manganite. If these films are under epitaxial tensile stress, and the resulting strain would be of the order of 1%.
Okay.
Concrete.
Yeah, okay. So very good. At least let me give you my viewpoint on one aspect of this. So, okay, so one of the things, and we're doing it too historically, is we think about using different substrates. We grow kind of in the same conditions or at the same time, and in an attempt to use the substrate to be my strain tuning axis, right? So one of the things that we've been long worrying about or thinking about is kind of free energy of defects. So particularly for ionic systems, there can be a dramatic change in the free energy of a defect, right? So let's just take a simple-minded picture. I have sodium chloride or something, right? Then I pull out one of these guys. Generally, these things expand because, right, you have this direct Coulomb, right? And so in that kind of cartoon language, you can imagine, and people studied, there's quite a big, dramatic changes in things like defects and so forth. And so our struggle before was to say, if we wanted to go beyond kind of 1% strains, are we really comparing the same thing, right? Even though we grow with the same, because of these kind of thermodynamic considerations, it's very difficult to do. So you may say then, well, do you not have thermodynamics? The question is basically by going from growing at 800 degrees C or something and doing strain at room temperature or now at low temperature, then, the temperature entropy term is going small in terms of the energetics. And we're trying to understand to what extent we are in regimes where we can really take the same sample, all things being the same, and perturb it in elastic response so we can make that comparison. I'm not sure if I answered your question, but that's kind of what we're thinking.
I understood at least the point of possible relevance of the process at high temperature. Okay, thank you.
Sure.
Can I ask a question? Maybe I misunderstand it here. When you made these experiments in the end with the superconducting, when you cool it down, what was the substrate that you put your membrane on top? Kapton? Or?
Yeah, but it's kind of just hanging.
Because kapton will be very brittle at low temperature, no? What is the mechanism that hold the membrane on top?
Let me see. Do I have a good picture?
It's kapton, no?
Yeah, it is kapton. What I could say, there is a caveat. So one of our headaches right now is it looks like our membranes can elastically deform more or respond better than our carrier. So, at low temperature anyway, kind of 3% is the maximum, right? So our headache right now is, I believe that the oxide could do happily more, but the polyimide goes under plastic deformation at 3%. So it does embrittle a little bit, but anyway, it's functionally okay. And just to say that maybe on my computer I have a better picture. But so we're actually anchoring a kapton loop, little gizmos to anchor this down. And we're raising the stage or this part of the stage. And so it's kind of we have little rollers here in the corners. And so it's literally being stretched. So we have a long translation axis in the vertical and it's pulling this thing out.
Harold, I've found very intriguing that this decrease of the critical temperature with the uniaxial strain scales with a metal insulator transition in the normal state.
Okay.
I was wondering, is it possible that you're playing with the interplay between charge order and the strange metal phase? If you would apply the negative strain compressive instead of whether you would increase the TC and make it more metallic.
Yeah. So very good question. So right now can't answer you. I'm not sure everything will work, but if we can see the stripe phase in the ordered state by, let's say, resonant elastic X-ray scattering, then we might be able to chase it around. So, you know, a little bit painful, but I think this is worth trying eventually, right? So hopefully we could give you more or, you know, ask that question more broadly. The second one, I forgot already.
The second was whether you change the sign of the strain if you do it.
Yeah. So, you know, the headache is that, you know, I can stretch this, but I can't do this. But, you know, it's not impossible because it's kind of like these bending geometries. So here and there, you can find examples where people try to, you know, put something they want to compress in the inner ring of this kind of a geometry. So we haven't done, but I think it's not impossible, but certainly hard right now. Yeah, you're right, in the sense that both in the cuprates and we haven't done this dynamic experiment yet, but infinite layer nickelates recently, we've been able to make membranes, and you can kind of see passively a strain dependence from, you know, on and released. And so, you know, I think, okay, from a physics point of view, this is a very wonderful tool, but it somehow, you know, there is that, you know, you made things worse. Okay, great. So fair enough, yeah.
Thank you very much.
So thanks for this marathon. Definitely, I have to admit that 1 hour and 50 minutes for a marathon is a very good time.
Oh, yeah, thank you.
So just before the break, perhaps it's my last question. I would ask something very general.
Please.
For your modus operandi to make these freestanding membranes.
Okay.
I would like to ask if you clean the membranes after the transferring, and how do you clean? Because you know, you show in the last slide that you can also put top electrode. And then I was wondering if you clean before to put the top electrode. If you do the transfer in a controlled atmosphere or glove box or something like that.
Okay, very good. We don't have these fancy glove box arrays, so that was step one. So the second statement is I mostly sit at my desk now, so I can't even tell you faithfully what everybody's doing, but there are cases where we're using things like plasma cleaning and so forth. A typical situation is that, let's say for some of these carriers, you know, rinsing, acetone, that kind of thing, but, you know, cleaning up with ozone. I think you also asked me about electrodes. Well, I won't show you, but so indeed for the cuprates, we need to encase it with protective layers. So that's a little bit of a tricky, right? That you have to kind of etch this away with, say, ion milling a bit, right? So historically, we didn't care because you can just wire bond and crunch through everything, but that is a disaster for a membrane. So some of these things are involving kind of a little bit of a painful clean room process to take away that top layer to make then, you know, ohmic contact and then on top of this. So, you know, that's, I don't know, there might be a better way, but that's what we're doing. Right? Yeah.
Bonding directly with the PVM structure, you do not follow the captions.
I think that, yeah, so if I want to passively test a membrane, no problem. But basically, you know, if I do an ultrasonic wire bonding, I'm basically making a bunch of micro cracks. And so as soon as I strain this is just going to run off. Yeah. Sure.
Maybe one last question and then we will have to break.
Thanks, Harold, for these two lectures. I would like to put a question regarding the first part. Because you mentioned, you put examples of many different membranes that you have been able to grow using this method and this sacrificial layer. And you spend a lot of time discussing the elastic properties of the layer in some cases. I mean, a lot of stuff on the mechanical properties or the microstructure of the layer. But I couldn't get any hint about the chemistry of the layers itself. Okay. When you put your functional layer in water to dissolve the sacrificial layer, many of those compounds are extremely, very much reactive to water and to the moisture. And what happens with that? I mean, what happens in terms of chemistry, the surface chemistry of this layer, or even not only surface chemistry, but even the chemistry inside the layer? This is one point. And second, regarding this this example that you show us, this kind of Toulouse transition regarding as a function of thickness in which you start from a 3D metal, 3D layer, you have a three-dimensional range, and then slowly you reduce the lateral dimension of these crystalline areas. When reducing the thickness, you are competing the elastic energy of the 3D system of the very thick one with the final configuration of the extremely thin one. On this long way, on this process, can you assume that the composition of the sample remains fixed? Or when changing the thickness, you are also changing the composition of the film in the very same way that you answered one of the previous questions. So both questions, summarizing, are related to the chemistry of the films. Okay. One is related to the dissolution. I mean, when you solve the sacrificial layer, and then the second one related to the elastic properties of function of thickness if the chemistry of the sample remains the same. Okay.
Very good. Let me say, so certainly for anything that is moisture sensitive, we are always making that embedded. So for all the cuprates, first of all, okay, so many more things may be moisture sensitive than we realize, but the ones where we know this is a problem, like we've been playing with YBCO or 2,1,4 cuprate or these nickelates, we need to be very careful and serious about having a top and bottom encapsulation layer. And it has to have high integrity so that we don't attack inside. Now, the next part of your question, in some sense, is in principle, both processes are there, meaning I can also laterally attack. And in some sense, our soluble buffer layer, and let's say this is a cuprate, right? We're sticking it in water. It's kind of a rate equation about what's going in. And so I wouldn't claim this is 0 and 100% or something like that. It's more of a question of how fast you dissolve this and what is the diffusion or propagation of that chemistry in the layer you care about. That is actually, to address just that is not too bad in the sense that I can control practically the speed of dissolving this layer by the thickness of the soluble layer. You can really see, going from very fast to, taking days, depending on that thickness. So that I can geometrically control to some degree. And the last question I thought you were asking was, again, kind of whether the chemistry is evolving as a function of thickness. Hard to make a experimentally verified, clear answer. Maybe I didn't catch all of the points, but so what thin film people worry about, right? Whether there's some drift or diffuse, as a function of growth. But basically, whatever we grew hot and then consider cold, after that, room temperature water, I think it's really about this kind of diffusion and kinetics inside. Yeah, okay. I have some actually fairly directly related slides on my computer, so let me show you. But I transferred slides here, so I can't.
Okay, so let's thank our speaker again.
Thank you.
So now it's time for the coffee break. So you will find it when you exit the conference room on the right, and we resume at 11:30. Yeah.
Yeah, so welcome everyone to our third lecture of today. Before starting introducing our next speaker, I would like to make a reminder, especially for the people online, which is remember that you can drop your questions using this Q&A tool of the application. So if you have any question anytime, you can drop it here. We will try to address it later. And so now we can move to introducing our next speaker, which is a Professor Nini Pryds. He's a distinguished professor at the DTU Energy in Denmark, and where he leads a large and dynamic research group specialized in the field of functional oxides. He received his PhD in RISO National Laboratory Material Research in Denmark and was a postdoc at RISO in Oxford. And his scientific expertise centers on growth of epitaxial oxides, particularly focusing on the intricate role of broken symmetries, interfaces, and impact on magnetic, electronic, ionic properties. He's been pioneering the study of these interfaces by conventional epitaxial growth and stacking freestanding thin films. And his work has opened a lot of avenues for understanding and manipulating the properties of these complex oxides. He also has been received the numerous prestigious awards and grants, including the Fellow of the American Physical Society, and he's received of a highly competitive ERC Advanced Grant. And he also serves on various scientific advisory boards, including the IFW Dresden and Center for Energy Materials at the University of Cambridge. So it's a pleasure to have him, Professor Pryds here. Please, the stage is yours.
Thanks a lot. Yeah, luckily, I will on behalf of mouth. I don't think I will survive my whole mouth, but I'll start with the next. One of which I was okay. It's better, no? In fact, battery is the next project that I have to make a battery out of this freestanding membrane. So trying to see whether we can make it better than what it is today. So I started to say tomorrow I will talk about freestanding oxide membranes, twisted membranes, and today I will try to follow up on what Harold was talking strain, and I will continue and talk about curved surfaces. In fact, the picture that you see here to the left, to the right, is a strontium titanate on a curved surface. It's exactly where Harold was finishing about the ability of tuning the material or tuning the strain, in that case with a predefined substrate. So this is one of the examples that I'm going to show now. This is not working. Okay, good. And I want to go also a little bit into the methodology, because I think, in my opinion, how to produce the material, how do you make sure that it's clean or not clean, or how do you release the material? This is part of the job, and without having a good membranes, I guess it would be difficult to get the result later in a better way. So I will talk a little bit about that. These are the people which contributed to the work that I'm going to show you today. These are the funding agency. And these are the international collaborators who contribute to the work that I'm going to show you today. So I would like to start by saying that the goal that I see it, and everything I say here is what I say. It's not what everyone will say, but I will stand behind what I say. And this is the goal. The goal is to create a controllable strain to induce a global or local modification of material. What I mean by that is we want to change the properties of the material by designing the surface, for example, the underneath surface that we want to put the material on. And then why oxide membranes? Why oxide membrane at all are suitable for such a modification? And there is many reasons, and I've chosen to put only two of them, and I'm sure some of you will see it with other reasons. One of them is that even small deformation in a well-defined position can impact the properties. It's a statement that I'm saying, I will try to show later. And the other one, that they can sustain considerable strain that surpasses that of the bulk material. And I think that Harold showed earlier that you can get strains of many orders, which otherwise the bulk would just collapse and break. So these are the reason why I believe membranes are suitable for such an application. And I want to start also with this paper or this graph that you see here. So this is a known phase diagram of the strain strontium titanate. So the strain is in the x-axis, the temperature in the y-axis, and in between there is the changes of the properties of the material as a function of the strain. This is well established, and I think people also recognize many of these effects that happen in this phase diagram. However, part of the phase diagram is inaccessible to us because of the strain. So if we want to go to higher strain like 8% or 9% or even 7 or 4%, we need to think differently, because what they did here is mainly tensile and compressive strain that generate this diagram, but we can also engineer the substrate, and we can also take the membrane and engineer the substrate and induce new type or other ways of creating a strain in the material. So what this diagram represents is basically an in-plane loading. So you can tensile it or compress it, and you can measure. But you can do some other things. You can take a curved surface, either a bubble or wrinkles or whatever you want, or pattern surface, and you can put your membranes on top of it, and what you get a gradient of strains. And when I'm saying gradient of strain, I basically mean that we get a flexoelectricity in the material. So this is a paper from Gostow. The reason why I chose this one is just to illustrate that what we get a strain gradient. Basically, we break the symmetry by having a shape substrate. And when we break the symmetry, what we are doing, we bring about, for example, flexoelectricity in some material. So we can take a material which is centrosymmetric and break the symmetry and get the material to behave as ferroelectric, while the material by itself is not ferroelectric. This particular paper was also interesting. It was about strontium ruthenate, metallic, and they broke the symmetry by bending the material. So most of the effect that happen on these curved surfaces is due to flexoelectricity, in my opinion. So there is other example in the literature. For example, this paper where the authors took a membrane, they put it on a cavity, they put a pressure below, and when they apply pressure, they could tune the strain of the material by the pressure below. And when they tune the pressure, what they did basically is look at the transition from antiferromagnetic, or the evolution of the antiferromagnetic properties of iron oxide as a function of pressure below. What I want you to remember here is not the physics around it, but the method that they've used. They've used a cavity and apply pressure, and then they constrain the membrane. In another work, what the author did, they took a membrane and then they just bend it. And they bend it so much that I think it was bismuth ferrite or strontium titanate, both of them they use. And when they bend it, they could get the enhanced polarization due to the bending of the material. So you can bend the material, you can apply pressure. Basically, these are some of the things that I showed before. You can tune it in different way, and you can induce strain in different ways. I want to go one step back and show you another way of making freestanding membranes. What we have seen today and yesterday, that there is a wet etching. Basically, that was the talks of early today by Harold. We have yesterday heard from Jacopo, and also, also today. I'm jumping to the other side. Oh, sorry. I told you I'm very bad in such a thing, so I need to. My mind is not always coupled to this one. Anyway, so the wet etching is what you have today. There is also mechanical exfoliation. This is basically when you take the material and you peel it off after you put graphene on top of it. And but there is another way of doing it, and this is spalling. So what is spalling? Spalling is a way of when you grow material, normal epitaxial material, after a certain thickness, what happened, the strain that formed in the material caused the material just to delaminate from the substrate, and then it's formed flakes out of this. So this work was initiated by Fabio Milato in Nepal, and we follow together with him. And what we observe is that at the beginning of this is LAO-STO. This is the well-known LAO-STO, and Hwang, who initiated many years ago, have also created a lot of people working on this area. So you make people work for the last 25 years on this topic, and among others, because it's so interesting, one of the things that we have looked at is what happened when it became a flake. And the way to do it is the following. So this is how it flakes. So at the beginning, it's growing layer by layer. So we know it and grow it after about 80 nanometer. What happened? You get cracks which are perpendicular to the surface, or parallel, so perpendicular to the surface. And after 180 approximately nanometer, we get some cracks which are parallel to the surface, and then you get detached a membrane out of it. Interestingly, those membranes are detached in the crystallographic direction of the crystal, so you get a well-defined crystal out of them. When we make a cross-section of this crystal, we see that they are intact. The interface is still the same interface as we know if we grow LAO on top of STO, so everything looks the same. By the way, this type of spalling have been known for years in the electronic industry. This is the way that they are doing a very thin layer of silicon. So they're putting a nickel, a stressor nickel deposit, and because of the stress, the material just detach from each other and form a very thin layer of silicon on this. So it's not new what we're doing, but this is at least new for us when we first observe it. So we can see that the material is the same basically as if we grow it epitaxially on top of strontium titanate. What we did, we took one of the sample and we did the device out of this. So this is two-terminal device, and we have a backgate here, which is the silicon P-type. What we measure is not surprisingly, but we measure metallic conductive, which is what you expect also from the LAO-STO. So nothing new about that. When we put the gate on it, we can see that the conductance increase here, and that means that we have a negative charge electrons, which is also n-type conductor. We know about it. So everything is the same. There's no new about it. The only difference is now we can make it as a flake. And then why and what can we use it for? So this is a little bit a vision and a little bit experiment. So what you see below It's experiment that we did. So what we did is also we tried to trench the silicon here. So when we trench the silicon in a certain size, we can basically predetermine how the size of the membrane will be. So doing that, we can pattern the STO. And now it's a vision. So we are currently trying to do it, but this is just for you. It's a cartoon, basically. So you can start with the patterning of the STO, as I'm showing here. You grow the material, then you stamp it, you sample it, and you move. I have to point here to get there. So you sample the material here, you take the flakes from the substrate, you're going and put them onto silicon, for example. Then you do lithography, you connect this, and then you get oxide electronics. Interesting about it is now you have a 2D material, 2-deck material, which have many, many properties, and now you can make devices out of this. So this is just an illustration how you can use these membranes or another type of membranes for some applications. I don't remember who someone was asking about where is the future of oxide electronics. So there is many futures to this. One of them, it could be, is now we can remove it. Now we can remove a piece of the material and put it wherever we want to put it. Okay, I will go and continue, and I will go back to the wet etching. And the reason why I'm going back, I want to show you or discuss with you a couple of things. In my opinion, some of the challenges that we still have with the membranes are the following. We still need to achieve a defect-free membranes. So many of the membranes that I've seen or I've observed, at least in our place, and I think it's true for any places, is that they have defects, and they have many defects. And we need to learn how to avoid these defects. Then the other thing is, if we want to use it to some application, we need to think about large-scale membranes free of defects, which is challenging. I mean, whatever I'm saying here is not something trivial and require a lot of work. The third thing that I think it's important, and we discussed a little bit about it here today, and I know that Jacobo discussed about it also yesterday, it's the cleanliness and the surface termination. These are absolutely important. And we cannot ignore it, because without having a clean surfaces or certain termination, I think we will not be able to repeat some of the work that we are doing in different labs. And the other points, which also was discussed a little bit, what about releasing with different agents? Some material cannot tolerate water. What would we do? I mean, how can we overcome the problem of water, inducing water to release the material? What should we do? And the last point, which I want also to share with you, I don't know if this is absolute important, but I think it's interesting. And this is about the shape on demand. So can we make a shapes? Right now we make a membrane and we transfer. Can we make other shapes and can we transfer them? And I will try to go to some of them. I don't have a lot of time, but I will try to go to some of the details here and show you some results, and hopefully I can give you some ideas what to do better. So I'll start by looking at the strain effect. So Harold was talking about it. In order to make a good membrane, in our opinion, we need to be able to tune the sacrificial layer compared to the layer that we put. So we need to find the right condition. Tuning them, I mean by strain tunability. So what we did is basically repeated what maybe other people did or thought, and we did it systematically. We tried to basically dope the material and dope it through all the way. And we could see that we can tune the material as expected. So it's nothing surprising here, but we wanted to do it systematically in order to understand how to get a good membrane at the end of the day. That was the goal. So we did many other experiments here. So one of the things that I don't have time to go through all the details here, but the thickness of the membrane, the thickness of the sacrificial layer, the type of polymer, the thickness of the polymer, the release time. So you can see there is many effects that can affect the quality of the material. For the STO, we found conditions which are good, and but it's a material dependent, in my opinion. You need to think about it. It's not one which fits all. You need to think every time you use a new material, you need to think about what will be the condition in order to get the best membrane out of it. I don't know if I can make this video work, but yeah, we were talking yesterday and today about how the membrane release. So what you see here is just the release of a membrane. I don't know if I can go back to it. And that was, oops, that was accelerated. Anyway, yeah, if I can go back to it. Anyway, what I wanted to show here that one, you have to think about how to release the material. So releasing with water is okay. It's necessary because water is what we're looking at. But also, if you notice here, we want the water to access the membrane in all sides, and we want it to access homogeneously, because if it's not homogeneously, it will break and deform. So this is one of the things that we also looked at about the how to cut. So what you see here is just a cut in the material, and the cut that we do is in order to allow the water to penetrate homogeneously into the material. Then come, of course, the question of the thickness of the layer that you dissolve, and that's bring me to the, yeah, I'm in there. Oh, now we see it once more. And that's bring me to another experiment that we are doing and finalizing recently, is trying to understand the dissolution time and how the dissolution time and the type of the superficial layer affect the quality of the membrane. I say something big now. So what we did is we tried to change the oxygen, the partial oxygen pressure of the growth, or we fix, in fact, the partial pressure of the superficial layer to 10 to the minus 4. And it was not accidentally, we checked it. The reason why we choose 10 to the minus 4, because we wanted to reduce it. Is there any problem? No. We wanted to reduce the material because we believed, I mean, the hypothesis was that if we create oxygen vacancies at the superficial layer, it will dissolve faster. That was the hypothesis. And then we grow the films at a different partial pressure. We put it in the water. We measure the time that it's dissolved, and then we look at the membrane and we characterize the membrane. How good are the membranes? And some of the results that you see, I'm not going to go through all the results, but we can see that the different pressure, for example, this one 10 to the minus 1, was it 10 to the minus 1? This is for LSMO. If you grow it, so this is 10 to the minus 1, by the way. So the LSMO will go as not layer by layer, but as an island. So is the STO, if you grow it in another condition. Keep in mind that the surface, that the SAO has 10 to the minus 4. So we looked at the material from the structural point of view, but what we characterize here is that the dissolution time as a function of deposition partial pressure. So what we see that there is an increase at the dissolution time as we reduce is the question there?
Yeah. One question.
Yes. Yes.
Let me check. Sound was yeah. This is a question from Rahil Haria. For target synthesis of the cation substitute SAO, how did you alter the process of sintering? Were there any difficulties that came with that? And for super tetragonal SAO, do you think this cation substitution could work similarly?
So if I understand the question is how do we prepare our targets, basically? So. And the way that we're preparing it is by normal solid state reaction. So it's nothing special about it. I don't know if I have to go into much detail about what exactly, but it's solid state reaction that we do it and do the pressure. We also approach other companies and try to buy from them just to compare, because at least our experience is that not everything is the same. So you can buy from one company a target and you can buy from another one, and you put them together and you see that the dissolution time or the release time is not the same. And then you have to find, it's the same with this crystal that we buy. We can buy one crystal from one company, another crystal. You want to do the same and you find that the crystals are not exactly the same. So all of these problems exist. I'm not underestimating them. They are there on top of all the other problems that, or challenges that we have. Anyway, what I want to say here that the dissolution time depend on the partial pressure. And at the pressure of 10 to the minus 4 and a growth of 10 to the minus 4, we got some of the good conditions that about the membrane. When I say good condition, and when you look at this, you tell me, okay, what do you mean by good condition? And the condition, when I'm saying good condition, for example, for the LSMO, we did also some characterization. So we look at the magnetization before and after, and we can see that the properties are the same. So we had to characterize them beyond just look at the substrate and do the same thing. And look at the substrate and just determine by the size of it or by the fact that you cannot see and I cannot see from here whether there is a crack, and there is a lot of cracks in some of them. So one of the characterization technique means for us was to physically characterize the material and also do the AFM. Now I don't have a lot of time to go into details. What I want you to remember is that we think that the dissolution time depends on the amount of oxygen vacancies at the strontium aluminate part. So if you're able to put enough oxygen vacancies, then the dissolution time will increase. Now, faster dissolution time is also not good. So you have to find the balance between the speed and the quality of the membranes. Yes.
So if you increase the number of oxygen vacancies, would the cell parameter of the sacrificial layer change and affect the strain of the uppers?
Yeah, so what you see here is basically, now to make sure I'm, so what you see here is basically the films at different pressures. So that's what happened. I mean, if you look at this is horrible, and it's repeatable. So it's not just one or two. We did it a couple of times to see that. So there is a relation between them. If it's going too fast, if it's going too fast, in that case, it's too fast. It's depending on also on the size of the membranes that you're cutting it from. If it's a large and you have too fast, then you probably get other things. So it's for these conditions. If I to say yes.
What's the difference between the two STO?
They are the same. It's just different results that we get for the same STO. So it's varied. My point about it, it's not one that all the time go the same. So these are the same. In fact, they're made in two different chambers, and
They're not the same.
No, okay, that's what I mean. The same STO, but it's different. Just to show that the process is not the same always. So if you're going to make tomorrow STO with a different pressure, I'm not so sure that you will get the same dissolution time. You will get the same trend, I believe, but I'm not so sure that you will get the same values. And basically, this is what I think. It's a very, I will not say place determined. It's a very chamber determined to some degree. And this is the way it is. I think this is my feeling at least. Okay, I'm trying to move to the next slide, but I cannot. Something is stuck here. Oh, yes. Okay. So let me move a little bit further to water. So what we want, we ask ourselves the question, can we avoid water? Of course, the question was a trivial question because you can avoid water, but what kind of way to avoid the releasing of the membrane with water? So there is, to my understanding, there is three ways of doing it. The first one is by exfoliation using the graphene. So, good. The first one is using a graphene. So this is remote epitaxy. So in this way, you don't need to use water. Yeah. You can also use the lower part here when you use another etchant to etch the material. For example, if you use LSMO, you use another etchant. However, you dilute it in some water. So there is water a little bit. So, but there is other etchant, of course, that does not use water. One have to think about it. So you have to find a way with an etchant which is not include water. There is a third way that I want to show you here is using the membrane as a template to grow on top of it material. But in that case, you don't need water anymore because you grow it directly with the PLD. And we did it together with a group in PSI. And what we did is we took a silicon, we put on top of the strontium titanate, and then we took it was in situ in the ARPES, so we can put it in the ARPES and look at the electronic structure of the material, and it looks as good as if you look at a single crystal STO. So what we did then we took the STO, we put it into the chamber again, and there is a PLD coupled to the ARPES, and then we deposit the following material. So strontium neobate, strontium vanadate, and iron selenide, which is a superconductor. And what we observe is that we got the electronic structure of the material. We didn't look at the properties, I must say. So we only look at the electronic structure of the material while they were inside the chamber under the same condition. And what we saw here is that the material behave as good as if you grow it directly on a single crystal of strontium titanate, which is interesting. And in some cases, in fact, it was even better. So the take-home message for it is that we can use the STO as a template, as a universal template that you can use it, for example, on a silicon, and then deposit whatever you want to put on top of it. You can avoid water, of course, but then you have to use the PLD again. And the other thing is that you can use it to integrate it with material which otherwise you cannot integrate, like silicon. Okay, and this is another way about the strain that we looked at in the barium titanate. So what we did is we did like any other people do. We grow the barium titanate, we release it, we transfer it, we put it onto strontium neobate, and then we took it to the beamline in Lund, in the MAX 4. It's a nano beamline, and we looked and investigated the material. I will come in a second what we have seen. We also did TEM, and we did PFM on the material. Our findings are the following. So these are just, this is the S-grown, this is the transfer, so we can still see the terraces after the transfer. I guess you can see it here. And the interesting things that we observe from the X-ray is that we can see modulation at the X-ray. So these are scattering signals from the X-ray. So these lines represent a scattering signal from 0 to 0 BTO. And then the question that or the first thing that we thought, okay, maybe we can see a domain structure in the material. So what we did is we took the material in the chamber here, and we heat it up to 200 degrees. Nothing happened. They're all the same. The distances remain the same. Everything is the same. Nothing changed. And then we thought, okay, maybe it's not a domain because you were supposed to see some changes at about 140. So maybe it's not the case. Then we took it to the TEM, and we look at the TEM. We can see still a modulation in the strain of the material. So we can see differences. The material, we try to do PFM. Globally, we can see that it's ferroelectric, but locally we could not identify ferroelectricity on this line. Cut the story short, the thought is like this. What we think it's happened is like this. We grow the material on top of STO. STO SAO and then the BTO on top of it. So we think that what happened is you get a replica, and I showed it before here. You get a replica of the terraces already on the BTO. And when you take the material and you put it on the substrate, it just relaxes. It's relaxed a little bit, but there is still some residual strain in the material, and the residual strain, that's what brought about, we think, that was brought about this modulation in the line. And this is our hypothesis. We cannot see any other thing. We tried it also, and we think it is the right thing because we tried it also with another miscutting angle of the material. So when you change the miscut angle, we get a broader width, and it corresponds to the width at least. Then I'm coming to the shape transfer on demand. And the question that we ask here is also, okay, we can make a material, we can make a freestanding membrane, and we can transfer it to any substrate, which is okay. And if we want to make a device, we take it to the clean room, whatever clean room you have, and you do lithography, and then you end up by something. This is a whole bar, for example. So this is one way of doing it. But then the question comes, what if you want to do two different materials, not the same material, on the same substrate, a different orientation? What would you do? You cannot do it with lithography. You cannot do it other ways. So the way that we suggest is we're using a mask. So we're using a predetermined mask, and then we deposit it through the mask. We're getting the shape that we want. Then we release the shape, and then transfer the shape onto whatever we want to do. So this is a shape of what looks like whole bar. So this is because that was the mask shape. So it's just a replica of the mask. We could take one of these whole bars and put it on a silicon. So this is on a silicon. We put leads onto it, and then measure whatever we want to measure onto it. Now, some of you with the good eyes could see that there is a defect here, and there is defects here, and defects all over, basically. I don't have time. You have to trust me. These defects are exactly a replica of the defects coming from for the mask. So in the paper, we just put them together and just show that it's replicate exactly the same. Just the defect, when we prepare this mask and the mask were prepared by laser cutting, you get some defect, and the defects are replicated by the device. That was strontium titanate doped niobium, and we cool it down and we measure the properties. It's exactly the same as we compare with another material grown on top of on STO normal material. So it's a way of having materials on a different shape, a different orientation also, which could be interesting for many applications, in my opinion. I have no idea about the time. I lost contact. I want to go a little bit further with the patterning, and Harold I think you showed this paper. I'm not so sure, but something resembles this paper. So what happened is people observe it. People who did MEMS for many years have observed this behavior for many, many years. What happened is that you get you take a membrane. These are metallic membrane. What you see here, you make a membrane on top of a window of silicon. And what happened? The material tried to relax, and it's relaxed by forming a buckling mode. And this buckling mode is not arbitrarily. These are well-defined. It depends on the thickness, depends on the shape of the material, and depends on the material that you want to do. So for a circular, you will get some buckling mode in this way. And for a square, you will get something like this. And in fact, people, including ourselves, we did some work many years ago when we did some work on the micro solid oxide fuel cells. What you do is you grow a YZ on top of silicon, then you etch the silicon below, and then you can see that the material buckled. And it's buckled exactly the same way as a metal. So there is a relation between the buckling of the material and the film that we want to grow. And the question that we ask, what happens if we use it for, when we use membrane on top of it? And that's what we did. We took silicon, we shaped it in a different shape, so square and ring circle and hexagonal and whatever shapes we could make in the with lithography, and then we put the membrane on top of it, and we observe some different buckling modes in the material. Now, what you can notice here is that some of the shapes are just standalone, and some of them have some white things coming. So these white things is the wrinkles in the material. So when a wrinkle meets one of these shape, it's initiated the buckling to start with. So this is not the real mode that you want to see. You want to see a mode which is independent and there is no buckling around it. So we had to separate them, but it's interesting to see that what the wrinkles do to the material. This is the circular shape, and what we did also simulation, and we could simulate exactly the same shapes as we observe in the membranes. Now, that was interesting. We observed something that somehow we thought that it will happen because there was no reason why not. What's interesting is that if you go to a smaller size, even smaller size, and these sizes are less than 10 micrometer, we observe that the material became flat almost, regardless. So this is membrane on top of this. You can see some defect here and here, but these are flat membranes. The same is the square and the triangle. So there is a critical thickness, we think, and we are working on it currently. There is a critical thickness which below the material is still flattened. Maybe it's because of the material itself, and we are trying now to look at the different material, different thicknesses of the material, and to see what are the parameters which make this critical transition from being buckled to being flat. Maybe people have observed it also earlier, but we haven't seen any report on this. So for us, it was new that there is a critical thickness, which caused it. Let's bring me to another. So we talked about a cavity and things that you can do on a cavity. And Harold was explaining this paper when he looked about the bending and stretching of barium strontium titanate on a cavities that you have by a tip of AFM. So this is one way to actuate and study material. There is another way which was done here by Gustav and the other colleagues, where they saw that they could induce a photorestrictive effect in the material. So now you can have a material which is barium titanate, and which does not have any substrate below, so you can actuate it somehow. You can actuate it with a different way. One of the ways that they choose, and I found it very interesting, is photorestrictive. So with the light, you can bend it or not bend it. There is many other things in this paper. I just want to illustrate here that you can get many effects when you put membranes, for example, on a cavity on a non-flat surface, which I will show you in a minute. So that's brought us also, but we did it a little bit before. So what we did, we put barium titanate on top of a cavity. We put a barium titanate on top of membrane with the different shapes again. So it's different shapes. And what we observe is that we get different, the first, the second, and even the third harmonic oscillation in the material. So what basically we observe is how the material behave, and this is due to, I mean, you get these different modes due to a few things. You get it due to the size of the bore. You get it due to the thickness of the layer that you use, and the compressive strain that there is. So it's a combination of all of this. What we observe at different places on the membranes for a certain shapes. We have seen it also for circular. We've seen it also for hexagonal. We can see all the modes, at least the first, the second, and the third mode, and we can also simulate it. What we also did, and that was a work which we are doing together with Max Planck, What we also did is we tried to flip the material. So here is the first mode, which is it's going up, and you're coming with the tip, you press it, and then it's going down and finding another position, which is also stable position. So you can flip it at a different position. What we are currently also doing, we're using a PFM and trying to actuate the material, trying to find the resonance of each cavity, depending on the size and the shape of the material. And it's not trivial because these holes couple to each other. So when you resonate one of them, you get some effect from the others. And we didn't talk about it, but we saw that it was not, when we actuate one, we get different resonances. And we figure out now how to isolate the membranes and look at a single one at a time. Good. The other opportunities with the surfaces of the material is, I've talked about compatibility with silicon, flexible, but you can put it also on suspended. You can put the device that you want to have on a suspended area, and then you can actuate it. And I will show you some ideas about it, and I will also show you some of the initial results on a non-planar surface. So it's not anymore a flat surface or cavity, but it's a surface which is predetermined. So these are some of the work that we did to start with. We took STO, put it on silicon. So and then we wanted to create a 2-deck on the material. In order we tried to first of all to use LAO on top of it. We didn't succeed. We went back and we say, okay, if we put aluminum, a very thin layer of aluminum, and then oxidizing it is basically what people already did, we maybe could get the 2-deck in the material. So we did it. So we started to do all the procedure. And just here, I will stop here. And we had a problem. And the problem is the contacts. I think someone asked before in the other talk about the contacts. We try to make a bonding. It's not happen. I completely agree with all the bonding electrode. It just break. You cannot do it. You need to do something else. And the way that we did it is because we used to work before with Jeremy Levy, and he did the same basically. He used or many other people doing it also, but we did it for the 2-deck. So you can argon mill it, and then you metallize the material here, so you get a contact into the 2-deck if you put metallic all the way. And this is what we did. So what you see here is the contact, and you have 4 metallization. And each point, in order to make sure that we're getting contact to the 2-deck. So we did it, and this is one of the devices that you can see. This is a Van der Pau device that we did. So what we further did is we took this device and we did another device, which is whole bar device, and we compare it also with the bulk. So we did another sample, which is directly grown on the bulk. We put aluminum on the bulk, we etch it, we reduce it, and we got the 2-deck as you expect to do. The interesting things, or the challenging things here, I would say that the carrier density turned out to be almost the same. The mobility is, you can see, is lower compared to the bulk reference. And then we try to look for superconductivity. We can only get superconductivity here. We could not get it here. So we have something to do with the mobility of the material, which we need to solve. We think, and we are still trying to understand, we think that it's something to do with a layer of polymer layer, a very tiny residual of polymer layer or any other contaminant that we have on the surface when we transfer the first layer to put it. So we need to clean it. We need to make sure that it's clean, because if it's not clean, we think that this is what reduces the mobility. Nonetheless, because we are putting it onto a substrate which is conductive, we try to gate it, to backgate it, but it's very difficult to backgate the material because the carrier density is quite high. So we are now trying to also to deposit. We're trying to reduce the carrier density and trying to optimize the mobility in order to see whether we can get at least superconductivity as other people. So we just want to replicate the same idea. And the reason why we want to do it is because we want to use it for a device in a cavity. So we want to put this material onto a cavity, and we want to put with the pressure on top, come with the pressure on top of this, and to induce strain to the material and measure the 2-deck as a function of the strain material. So basically using the same principle that we do here, but with the device that we can put it on a cavity. We started to do it here, and you can see these are the cavities. So we are working on it, but this is just a vision for the future that we are doing. Let's bring me to another story. I'm finishing soon. And this is about curved surface. So there is a paper, there was a paper, and there is other papers. I'm just showing this one. This paper of the group of Nini. And what they did, they put a membrane on top of polymer, and they basically stretch the polymer or contract it, and they get wrinkles. And they use the wrinkles, and they do PFM, and they saw that the material responds. So there is a response of ferroelectricity, or at least a response from the PFM when you strain the material by forming wrinkles in the material. In another paper here, people predict some of the effect that can happen in freestanding membranes. So if you have a freestanding membranes with different shapes, they predict that you can induce the ferroelectricity due to the flexoelectricity, basically. This is what motivates the results of the ferroelectricity in the system. So with these two examples, we went and we said we took these are gallium arsenide nanowires. So we had some nanowires that we had in the lab, and these nanowires are either situated around in a circle or linearly, and yeah. Oh, yeah. I don't know. Yeah. Okay. So we put a membrane on top of these structures, and we looked how the structure conform. And this is just an illustration from the AFM how the structure conform on these nanowires. So this is a real picture after we measure it. And we can see that we believe, and that of course there is some strain gradient at the tip here, and there is no gradient here. The whole idea was we try to create a strain gradient in a place where we can measure the changes of the material. If we take STO, for example, this is what we did. We took STO and we wanted to see whether we can induce ferroelectricity due to the flexoelectricity. So that was the original motivation. So this is an interesting picture, in fact. When I saw it, I think I like it very much because it's showing the membrane on top of the nanowires, but you can see the terraces, and the terraces follow all the way. It's not broken. It just conform all the way over these membranes, over these nanowires. So we measured the strain, and here we could get from our calculation a strain of about 1% at the top. So it's not huge, but we know at least where we are, what we will look for. So it's a 1% strain. And that's bring me to other paper that will explain later the result that I'm going to show. So I'm going back to the same paper that I showed before, 1% strain. We expect to see ferroelectric phase. Remember, this phase diagram was made by axial strain. So when we do not have an axial strain, so we have another situation. I just want to put things in sort of perspective. There is this paper that Harold just explained before, and I'm not going to repeat, that was also done by compressive and tensile strength of the material and induce of ferroelectricity. And there was a paper by Cheng bomb, where they see, I don't know if you can see it here, where they claim in the paper that they could see changes in the Raman from the second mode to the first mode. So the first mode is forbidden in this material, but they could see the second mode. The first mode they saw only when they strained the material. So taking this into account, what we did is we took our nanowires and we looked at different positions, A, B, and C. A and C are equal. These are the flat surfaces. So A and C, we see no signature. And B, we see a signature at the right position of the first order Raman mode. We think that it is like this. We're still trying to understand the effect, but when we did the tip-enhanced Raman on the sample, what we get, we can see that the response of the Raman is different, at least when I'll show it here easily. Yeah, here easily. So we see the different response, and these lines, this slide correspond to the first order in the Raman. So these are indication. We try to measure with the PFM. It was impossible for us to detect any response from it. We think it's too weak. 1% is very difficult to see. So we are still looking at this structure, but we moved a little bit further. We ask ourselves, can we make it even higher? I mean, we need higher strain. If we want to really clearly see, we need to go to higher strain. What we are doing is we are using a nanofraser, and I don't know if some of you know about what is nanofraser, and I do it very briefly. I know the time, way beyond the time. You have a resistant. Here we have the STO silicon, and if you come with a heated tip, you can basically form whatever shape you want to do, and if you etch it, basically you get the same shape that you want to do. People can do with this one different shapes that you can otherwise cannot do with normal lithography. Oh, it's very difficult, like a dome or like a saddle or cylinder. But you can do it with this technique. So what we did, you can do some other things. So these are real samples that we did. And this is a quasi-crystal that we can also do. So basically what we did, we put the membrane on top of the material. We can see that it's conform. We can measure the amplitude. Everything looks the same. So it's conformed really good along the material. What was more interesting was to measure the strain on the material. And here we can get 4% strain. And 4% strain, this is a little bit more promising. I cannot show you results, so I disappoint you already now. We are working currently on measuring with the PFM, and we believe that 4%, we should be able to see some results on it. The fact is that we can tune it. This is interesting. So this is a sinus curve, which is a normal sinus curve, and this is decay sinus. So we can change the amplitude, we can change the wavelength, we can change the material as we wish. And this is for curiosity. When we put the material, these things that does not work, and I think it's interesting to show it also. So when it's work, it's following this, but when it's not work, it's just lying on top of it, and it's not conform anything. But you can see interesting things that the material break, and detach from each other, and it's formed like lines, like a point here. And I can show you. You don't try to see whether this line corresponds to this line. They are not. We don't know what is it, but it's interesting to know that the material can break in such a way that they detach from each other. So this is just for curiosity. I don't want to show. And the other thing is that we also put membranes on a quasi-crystal made by us. And what happened is that the material break. So you can see it just break there. So we think that, but yet you can follow still the place where you can get the structure of the material, but it's break on the point. So we are now playing also with the thickness, with some other parameters in order to make it conform onto the substrate. Final slides is that there is many things that we could do, but there is another thing that we could also do is making many devices from the same growth. And what you see below is one piece of membrane, and you can see how many devices we could make on the same membrane. So it's amazing. We can play with this as we wish and do many devices on the same membrane. So this is another opportunity, in my opinion. And with this, I would like to thank you, and I'm sorry for the overtime.
Thank you. Thank you, Professor, for a very nice talk. I think we have some minutes for questions. Any questions in the audience? Paco?
Thank you, Nini. I mean, very stimulating, a lot of opportunities, very exciting. I have a question. What is the maximum in these last structures, pre-pattern substrates that you were showing, which is the maximum strain gradient that you can generate? Not the strain, but the strain gradient.
The immediate answer, I don't know, but it can be, we can tune it. I mean, we can make a form which is higher than that. So the question is which form can give you the highest strain? I cannot give you numbers now, but I believe that we can get it higher if we find the right. It depends on the radius of curvature material. I think what's interesting for us was also not just a strain on a wavy material, but I think what we really want to do is on a dome, because then we have the curvature which supposed to conform all the material, and there where we want to see how membranes conform a dome, and whether it's break or not break, I don't know. But the radius, I think we can tune as long as I mean the equipment. I mean the way that we're doing it is unlimited. We can do as much as very small sizes.
Can you guess the sign of the flexoelectric coefficient of the STO?
Guess this, sorry.
Whether it is positive or negative?
I would think it's positive, in fact, but I'm not sure.
Okay.
I guess. You asked me to guess, I guess.
Okay. Thank you very much.
Any more questions?
Regarding this LAO-STO flakes, which you have shown in the beginning of your talk, are these superconducting?
Yes, they're superconducting, and the superconductive temperature is about 500 millikelvin.
500 millikelvin, even higher?
Yeah, 500. No, wait a minute, 100.
Okay.
Millikelvin, yeah.
Okay, and how long it takes to deposit 180 nanometer of lanthanum aluminate?
Lanthanum aluminate? You mean aluminum? Oh, the whole film together.
Yeah.
I don't know. I don't remember. You mean the 180 nanometer?
Yeah.
I guess a few hours. I don't know.
Okay. I mean, so you use the same.
It's the same condition. So we just continue to do it. If this is your question, it's the same condition. I don't remember the number, how many hours it is. It's a long time. So we could follow the oscillation to a point where you can not follow anymore, but we can determine the thickness later.
Okay.
And we did it not on one sample. So it was Fabio who started with that, and then we took it over because we wanted to make devices out of this, and we were the one who's making the devices in my group together with him.
Okay, thank you.
Any more questions?
Very naive question. I'm not working on this regime, on this topic. When the people like you are doing the solvation of the sacrificial layer, and I clearly understand that you want to control this process, no? And maybe the way you are releasing the strain partially in some areas, where other areas are still with a fixed strain of the substrate. Are you or other people trying to do like a stamp from top that maybe can be like a hard stamp at some point, whereas you do the sacrificial dissolution and then try to control in a better way how you get out of the stamp, so the strain is fixed until you do the second step?
So again, if I understand you correctly, you ask whether we try to do the stamp exactly the same as people doing with the 2D material. stamp. No, this is what you ask.
Yeah, but what I'm thinking is that you can maybe try to have, or one can maybe try to have like a stamp that is like a clamp of the atomic positions. You get rid of the substrate, no, with a sacrificial layer solution,
Yeah.
and then you try to slowly, in a more controlled way, get out of the stamp.
Yeah, I will show tomorrow some of the results that we are doing, because for the twisting, you want to transfer it and you want to do it, and we using a stamp to do it. But saying that, it's not trivial, because you need to find the right polymer, which conform with this, can be released, and not stiff enough, not less stiff. I mean, you have to find the right condition. I think the people in 2D material have exactly the same, had the same issue. Here it's a little bit more because it's a more stiff material. So it's not trivial to use any polymer. You need to find the right polymer with the right condition, not to break it. But we tried, I mean, back to your question, maybe at the beginning, we tried to stamp it. We tried to take a material, we say, okay, let's just put a membrane there and stamp it and move it there. And we did it, and we could see that we can stamp some flakes of hundreds or tens of micrometers, but it's uncontrollable. We can move something. I don't know where it's taking off and where it's not taking off. So it's not something that we can work with. And we wanted to develop methodology in order to be able to do the things time after time after time. So, yep.
Thanks, Nini, for this inspiring presentation. I have a couple of questions. Yep. One regarding at the beginning, you mentioned some two decks that you formed using STO and LA on top. And in the continuous film, it turns out that the mobility was very high, but in the small flakes, the mobility was very low, about 25, something like that, I think, the mobility, no?
Yeah.
And I think that you mentioned that you guess that could be to the polymer that you have used and residuals of the polymer.
Yeah.
I really don't understand how the polymer can modify the mobility of the two deck. I mean, the two deck is the two deck. Why the mobility depends on the polymer? This is one question.
Yeah. I can maybe answer this question.
All right. Okay. Then I will come to the second.
I will not forget the other ones. So there is two different. I mean, at the beginning of the talk, I talk about LAO STO. This is something else, and later in the talk, I talk about STO, where we put aluminum, and then oxidize it. Okay. So how do we do that? We take we take material which we deposit onto a sacrificial layer with the polymer on top. We release it. We take this material, we put it on substrate. In that case, was silicon, and then we remove the polymer with acetone. We think. And then after we think that it's clean, and acetone and also plasma etching, we think that it's clean, we deposit aluminum on top of it. And I think at this point, we already have some residual of, so when you put already aluminum on top, the two deck is between the aluminum and the STO, because aluminum, it's take oxygen from the strontium titanate and from the two. But if there is at the interface, if there is already carbons or some other residual that we have, that might affect. This is our hypothesis. We're trying we cannot see otherwise. I mean, why does it happen?
Okay, and the second question is a bit at the very end.
Yeah.
You mentioned this substrate that you pattern in a given way, these beautiful shapes on the substrate, and you put the membrane on top. And the membrane somehow conformally covered.
Yeah.
And I'm wondering why the membrane itself conformally covers the substrate, why it bends. Why the substrate, I mean, the membrane is just not keeping basically flat on this ripple surface. Why it bends? Is a gravitational force, is a chemical force, electrostatic, what is in there?
Again, the first question, I don't know. The other question is that my thoughts about it is in some cases we can see that it's flat. So what I show in the end, also for curiosity, that it's not conform. I think it's something to do with the plasticity of the material. And someone mentioned about the superplasticity of this material, maybe at this. And if it is superplastic, then it will follow it. But I don't know. I don't know what are the conditions. We try also to ask what is the condition for superplastic effect in this material, because maybe this can help us understanding why does it form so fine on such a fine. It's impressive.
That's impressive.
I agree with you, but it does. It does this. So it's not, and we try to understand what are the conditions.
You know, like kind of
chemical, yeah.
Chemical, yes.
Yeah.
On the silicon dioxide, yeah.
On the what? On the silicon?
On silicon dioxide, I guess.
It's not silicon dioxide.
It's not silicon dioxide.
No, because we wanted to measure with PFM, so we are putting gold on top of it. Or we put gold, we put platinum, and so we're trying to modify the surfaces. In all cases, it's still conform.
Well, still.
But I don't know. Maybe there is chemical. I mean, how would you suggest to what should we? I'm open. I would like to hear if there is any suggestion to. I mean, we can clean the surface. We can plasma etch it. We can do many things that we think also of doing. But I have no clear idea what is that make it. So therefore, we want to go to surfaces that are really single surface, like a dome, and see how does it conform a dome. I mean, this is interesting question, I think, for itself, because then it's independent, and then it's whether it's still follow everything, or whether it's folded on the sides, or whether it's break also. But they are not breaking here, so that's.
Well, since I have the microphone, perhaps I can make a following up question, because I got really interested about this sacrificial layer. Well, sorry, it is a hard mask you are using for a whole bar pre-patterned. So perhaps I did not catch all the things, but I did not understood if it is pre-patterned, the whole bar shaped hard mask is made before the entire grow or after the sacrificial layer, or is it just something you slide in and the PLD and then you grow?
So if you didn't understand it, probably maybe other people also did not understand. Let me repeat it, what we did. So we started growing SAO, the material. So in the chamber, we go SAO, and then we stop, then we bring a mask into it, then we change the target, we deposit another material through the mask on the SAO, we're taking it out, we're dissolving the material, and then we left with this one.
So the mask is a metallic mask.
It's a metallic mask inside the PLD. In fact, the metallic and also ceramic, because we wanted to, because if you want to do some other experiments, you don't want metal inside, because I don't know, if you want to look for magnetism and you have iron in this, you want. So in principle, you can do any mask that you wish. We did the ceramic or metallic mask.
Okay, thanks.
Thank you. Very nice talk. When you were showing the membranes over the cavities, you showed that you had some backing, and you could switch from one state to another, so you have some kind of bistability. So is it possible to switch back and forth between these two up and down states?
It's possible if you can turn the material. We cannot extract it.
Right.
You can only push it.
Do you know why they show this bistability? What is the mechanism to?
I think because there is two states where the energy is the minimum energy. So either up and down. It's just yes. That's my feeling about it. In fact, it's interesting, just for curiosity. The reason why we thought about it, we thought about what if we can make a memory device out of this. So if you can have a device where you can switch it.
Like a ferroelastic.
Yeah, exactly. You can switch it and you can say this is on, this is off, but it's stuck. It's there. So that was motivated at the beginning.
What? Last question, maybe.
Last question? Okay. This is a question for the two speakers.
Yeah.
When you have these peaks and valleys, when you form these oxides, in the peaks or valleys, there are huge strain, no? Huge amount of strain there, localized.
Yeah.
You're talking about the elasticity or elastic. And what about the plasticity? How do you know that the stoichiometry doesn't change when the strain is so high and the properties of the material will change?
You're talking about the membrane that we put on the surface?
Depending on the angle, no?
Yeah. So when you say chemical change, why should they change? I will ask you.
Well, if the volume has to change so much,
I think what will change, I believe, I don't know, if you take a strontium titanate and you bend it or you strain gradient it, you will, I guess people show it here very clearly, that you will just shift some of the ions a little bit from their position. That's where reflects electricity. But why should you
Would
change?
you go farther and release oxygen or?
Okay, then you need, then I don't know.
Nobody has
maybe you're an answer. I have no idea. I don't know what, you need really a lot of energy to take
probably these oxides, when you, after depositing them, they already have oxygen vacancies, most probably.
They don't have, you say?
So when you deposit the STO,
yes,
most probably there are oxygen vacancies in this layer.
Yeah, but we also anneal it. So
okay, you do annealing afterwards.
Yeah, so we can, I mean, we anneal it, but you can also, just for a case of discussion, we can take another material. And we try with another material, and it still does the same. So the question is more basic, whether the composition changed, and I cannot see why would it change. I can see that
because the strain is so huge. If you reach 8% or even higher, I mean,
yeah, it's a gradient. So you mean that composition will change along the from what to what? I mean, let's think about it. Let's think about strontium titanate. Okay, perovskite, strontium titanate, and you increase the strain more and more and more. What do you think?
When you,
I'm asking you.
For example,
I don't know. I mean, I have no answer.
So you assume that the material is elastic, that the formation is purely elastic.
I think so. I think so because I don't have other. Maybe we should check it. I don't know. A way to check it maybe is, I don't know. What can we do? I mean,
there are no works reporting changes in the stoichiometry when they observed such a big strain gradients, no?
Not that I'm aware of, but maybe other people did, and I don't know.
Your questions are all, very pertinent. At least, as I told you, for reversibility, we're limited by. So these mechanical games were limited by the plastic threshold for the Kapton. And so indeed, I think, I think that's a good point, but I don't know, or we haven't experimentally addressed whether there are, chemical changes in the extreme regions. I think the other thing that your question motivates is that in the presence of some defects, whether you have the equivalent of electromigration, I think is what you're thinking about a little as well, right? I think at least I'm not aware of experiments, and we haven't done to try to do kind of microanalysis. The very thin membrane and to do chemical analysis is, with high precision is probably one of the challenges.
But I have an answer, in fact. I can give you an answer in a week if you call me again. And I tell you why. Because we are now doing a cross-section of these membranes with microscopy. We're doing TM with yields. That's what we're doing now because we want to determine what are the states of the strain states. So we want to map the strain states along this. I will be able to give you, we're doing also yields because we want to see whether the oxidation state of the material stay the same or not. So I will give you, I forgot that we're doing it, but we're doing it currently. So next week, probably we're going to have the results.
Okay, I think we can stop here. We are way over the time. Maybe we can thank the speaker again. Just a reminder for people who's not from the campus, where can you find what is this? Things here. Yeah. You can find these cafeterias here, the one who's not familiar with the campus. So you will find something to eat. Remember, we are resuming the poster session at 2:15.
And remember, now we are going together outside to take the picture. And then another announcement regarding the poster session that will start around, let's say, 2:15. But I think you should be able to post the poster already now. Yeah. So thank you.